Good morning, all the participants. Thank you all for joining last 2 days and making the session grand success. And I welcome you all again to the third day of the workshop on advanced materials for energy and environmental applications. So today is the last day of the session, and we still have some wonderful talks by the eminent subjects in the fields. And now, for the today's talk, we have with us one of the very vibrant and enthusiastic academician and research person, Dr. C.H. Shilpa Chikra. She is an assistant professor, chairman, board of studies of nanotechnology. She is also a nodal officer for Tech 3, Center for Nanoscience and Nanotechnology, Institute of Science and Technology, JNTU Hyderabad. She is working over there since 2002 to till date, and she did her PhD from JNTU Hyderabad, and she did her MTech also at JNTU Hyderabad. And she had several administrative positions other than the research and teaching positions. Some of them are she was the head of the department, and she was a board of studies, and she was a coordinator of tech, and her research specializations are in varied fields ranging from synthesis and characterization of nanostructured materials, biomimetic and biological inspired materials, carbon based materials, nanotechnology for agriculture applications, biomedical applications of nanomaterials, green nanotechnology, and nanomaterials for environmental applications. And she has many research projects completed, and some of them are ongoing also. She has done 4 TechWip projects, and right now 3 DST Serve and Seed and AACTE projects are going on, and several research projects are in pipeline. And she has awarded 568 MTech projects, and she has some of the foreign universities also visited. And to note, very importantly, she has 79 international publications and 9 published books and several conference proceedings and 2 patents. And she has MOUs with 2 industries, Nanospan India and Pioneer Food Solutions. So academics always attached with industries is a useful option, which she is wonderfully doing. And she has several members. She is a member of several professional bodies like life member of Indian Science Congress, Materials Research Society, Electron Microscopy Society of India, and several others, to name these other few. And I can say that she has conducted several research programs and conferences. ICON C 2014-18 and national conferences and workshops, to name, I think around 7-8 workshops were conducted. And she has also conducted 6 refresher courses supported by UGC. So these are very few of her accomplishments, and she is a wonderful speaker and wonderful researcher. I welcome you all to take this opportunity and listen to her and maybe discuss with her and utilize this in a best way. So once again, welcome you all, and I also welcome Dr. Shilpa Chakra. Please share your slides and can give her a wonderful talk now. Thank you.
Thank you, Mamta. Thank you for your invitation to this webinar. And I also thank the Vice Chancellor of Yogi Vemanna University, Registrar, and sir for inviting valuable webinar on advancements in energy and environment. So to begin with, Mamta, am I audible, clear?
Yeah, you are audible. Yes, clear.
Yes. Okay, thank you. My today's topic is on recent nanotechnology advancements in medical as well as in energy storage applications. So, why I have opted this topic is medical and energy are related to each other. So, I just wanted to show you how they can be related to each other and how medical fields can be more effective by using these nano energy storage devices. So, in this talk, we will discuss about a few basics of nanotechnology and how we can categorize nanomaterials according to their dimensions. We will also discuss why nano is uh, good or effective, or why small particles are very effective. And we'll also see the approaches of preparing the nanostructures, like top down and bottom up approaches. And we'll also see the latest and research trending biomedical as well as energy storage applications by using these nanomaterials. And uh, let us go through the future slides. Uh, so to begin with, comparison of macro, micro, and nanoscale. We have a question always, if at all macro and micro are already existing, but why do we have to always see or work on nanoscale materials? So, to begin with, if you see here, an average person height, which is of 5 feet 8 inches, is equal to 180 centimeters. So these 180 centimeters is equal to a 2 trillionths of the nanometer in size. When you see the size of an apple, it is in the size of 8 centimeters. So when it equates to nano sized, it is 80 million nanometers in size. And coming to an ant or an insect or any small creatures which we can see with our naked eye is about 5 centimeters, which is equal to 5 million nanometers. So, if we compare on a micro scale, the approximate size of human hair, or if you can take the corn fiber, the size of the human hair or a corn fiber is approximately equal to 80,000 nanometers. And the smallest which we can see with the human eye is about only 10,000 nanometers. And the bacteria E. coli, which is available in the water, is about 2000 nanometers. So when we come down to the nano level, or the bacterial level or the viral level, uh, the diameter of, when you can see here, the diameter of a DNA is only about 2 nanometers. So this DNA is very important in human life or to human ecosystem, because uh, DNA stores all the information related to the species. So the DNA is only about 2 nanometers, and if you see the cellulose nanofibrils, it is of about 3.5 to 100 nanometers in diameter. And if you can see the hydrogen atom here, it is only about 0.1 nanometer in size. And the trending pandemic or the COVID, which we all are facing, is also is in the range of nanometer. So we can see that how this COVID or coves are one, or the coming upcoming coves are two, are in the nano sized, and how these nano sized are damaging or affecting in very any kind of environment. So now we will discuss about how we can categorize nanoparticles into one dimensional, two dimensional, and three dimensional. In case of one dimensional, it is only one parameter, either length or breadth, are in the size of nanometer in scale. And the examples follows are the thin films, layers, and coatings. When you come into the two-dimensional nanoparticles, in this case, only length or breadth, only two parameters will fall under the nano-sized dimension. So examples here are nanotubes, nanofibers, and nanowires. And coming to the third example here is the three-dimensional, wherein all the three parameters like length, breadth, and height, all the three parameters are in the scale of nano-sized. So when you see the examples here, it is nanoparticles, nanoshells, or the nano rings. So these are the three types of categories where you can see the nanoparticles. So why do we need nano when we already have macro and micro? So what are the advantages of nanoscale materials are? Consider a simple example of a full shell cluster here. So the full shell cluster here, where we are having seven shells, the seven shells are comprised of 1015 atoms here. So the total atoms are 100 and so 1415. But when we count the surface atoms which are exposed are only 35. If the same seven shells are made into the smaller pieces, and then if you see here, if this one shell has a total number of atoms 13, but wherein if you see the surface atoms exposed is 92 percentage. So by this we can see if the surface to volume ratio, if it is increasing, there is much performance can be expected from the material. So these nano objects are having these properties. They are faster, lighter, can get into the smaller spaces as it has a very less number of atoms, and it is cheaper in rate and more energy efficient, and different properties are at very small scale. And coming down to uh, the types of nanomaterial here. The first one is the naturally occurring nanoparticles formed during the forest fires or volcanic ashes or viruses. So the naturally occurring viruses we are already seeing in this pandemic situation. And the second, these naturally occurring nanomaterials are in the range of nano size. And the second category here is a man-made nanoparticles. It may be incidental or engineered made nanoparticles. And examples for incidental nanoparticles are nanomaterials generated from cooking smoke and diesel exhaust. These processes emit some kind of nanocarbon materials, and these engineered nanoparticles are also a human origin, but we make them in the lab. So when you compare to the incidental nanoparticles as well as engineered nanoparticles, we also see here the core and shell type of nanoparticles observed. We can have the organic and inorganic coatings by engineered nanoparticles. Also, the examples of the engineered made nanoparticles are the metal nanoparticles, quantum dots, bucky balls or nanotubes, and sunscreen pigments and the nanocapsules. So, how to make these nanostructures or these kind of core shell or the metal nanostructures or quantum dots and all? So, let us see there are two main approaches in preparing the engineered or man-made nanoparticles. One is a top-down approach, and the second one is bottom-up approach. The first, we will see what a bottom-up approach is. Sorry, top down approach is, this top down approach is building something by starting with a larger component. This is a larger component of rock. When you carve it away, you get a sculpture here. So it is similar to making a sculpture from a rock. So here your rock is a bulk material, and you are carving out the smaller particles from the rock and making the statue. Similarly, nanoparticles are made from a bulk material by carving out. So this process is called as top-down approach. From the bigger sized bulk material, you are making a nano-sized material. When you see the next one is a bottom-up approach. For example, here you are building something by assembling a smaller components. So we are assembling the smaller components and making a building or a car engine. So we will have atoms and molecules, and we will assemble the atoms and form the nanoparticles. So it is called a bottom-up approach because from atom scale, it becomes nanoscale. And here, when you make these nanoparticles, we can make these from the inorganic or organic materials, or it can be a hybrid also. Like example, a combination of inorganic and organic together. The size could be between 1 to 100 nanometers. So this is the one categorization of how to prepare or how to develop your own nanostructures. So the first category here is your size. So your size should be in the range of 1 to 100 nanometers. So when you make these nanometers, you can make them you can have various biological material or organic inorganic together in a combination, or you can use some functionalization on the surfaces, like adding polymers to your surfaces to get activated, or you can attach some glucose molecules onto the surface atoms, and you can also work on the different shapes and structures of the material, and you can alter any kind of these four parameters to get your own desired compound. So let's begin with the main objective of this webinar. So in this webinar, we'll be focusing on the biomedical application as well as the energy storage applications in the future slides. So we have, when you see this pictorial image of various applications of nanoparticles, we have textile, biomedical, healthcare, food, industrial, electronic, environment, and renewable energy. So it has a vast range of applications falling into. And in this presentation, we'll try to focus on this biomedical as well as the renewable energy applications for in the recent trending applications only. We'll try to focus on. So coming to this, one by one, let us see the biomedical applications of these nanomaterials. The first application is that we can use these nanomaterials for the diagnosing various diseases, and we can make some fluorescent nanoparticles which can easily reach the tumor location, and then the tumor location can be accessed using the fluorescent microscopy or spectroscopy, and then you can locate the tumor area and then deliver the drug. The next application here is targeted drug delivery, and the main drawback of the traditional cancer therapy is that we are not able to specifically target only the cancer cells. The traditional drug will also kill the healthy cells, so damaging the other parts of the organ or the healthy organ. But by using nanoparticles, we can specifically make them go only to the cancer cell and kill the cancer cell. So we have a few techniques called hypothermia or targeted drug delivery, wherein that can help in killing only the cancer cells without affecting the healthy cells. So we can make these targeted drug delivery systems also using nanostructures. We can also go for tissue engineering by using nanoparticles. In tissue engineering, if you have damaged skin or damaged what do you say organ, we can grow that damaged organ or skin in the lab, and we can replace it in the body. And another upcoming area is organ printing or 3D printing. So by which we can print any organ or any cell which is required in immediate requirement wherever it is, we can go for the organ transplantation. So these recent advancements are under the clinical trials only. So a lot of research is going on about this organism. We can also make artificial cells in some cases when we don't need any complete organ also. Here we can replace only the damaged cells or dysfunctional cells. For example, if we want any to make an artificial RBC, it is possible by this artificial technology also. And this application, DNA nanotechnology or a protein nanotechnology, also comes under bionanotechnology. Here, we can use a DNA or a protein as a construction material, and also like a nano tool to make nano machines or nano devices. So these are useful for making biodegradable therapeutics and for understanding various diseases. And coming here, nano is not new to India or to the ancient time, because we have this medicine Bhasma, which is an Ayurvedic medicine that have a lot of metal nanoparticles, and a lot of research is going on to explore the applications of nanoparticles, and these Bhasmas are having various therapeutic applications. So the vast research is also going on to understand this ancient drug, how this is more effective, and where it can be applicable in therapeutic applications. Come to this upcoming research or area of nanorobots. To just think, we feel like it is like it may look like a science fiction, but a lot of research is going on to make it a reality. The idea of these nanorobots came from a bacteria. So this bacteria moves from one location to the another location by its tail. This tail is called as a flagella. So it has a tail where it helps in the locomotion or the movement of the bacteria from one place to the other place. So this flagella will help you in movement in the surface or movement in the any kind of liquid medium also. So taking this as inspiration, scientists have replicated or duplicated the creature of this bacteria, which has a flagella like a tail. They have prepared a robo here, which is called as nano robo. So it has a body and it has a tail for the movement. So this is how it looks. The nano robots, how it looks. It swims in the bloodstream. So it has two tails, which is replicated as a flagella. This helps in the bloodstream. And the nanorobot has a capacitor here. So the capacitor here can be of the recent energy storages, which we'll see in our future slides. So we can also implement the energy storage in this nanorobot also by replacing the nano capacitor. And it also has a micro camera attached to it. This acts as an eye of the camera for vision where exactly the robo is going, and for the movement or in the bloodstream to access to the location, the micro camera can be used. And this is the payload. Payload is nothing but the engineered drug or the therapeutic molecule. By means of the supercapacitor, the nanorobot will have the energy to move from one location to the another location. So it will move from one location to the another location, like to the arteries and veins, using the as appendages, and it can read the location and it can deliver the drug. So these nanorobots are also called as nanobots. So when you see this image here, the nanobot is coming and attacking to the damaged cell or the damaged article or a vein, and it is attacking the vein and trying to deliver the material to the exact location. So this is how the nanobots work. So still the research is very trending, and still the clinical trials are going on in this nanobots. Other than the nanobots are not only used for the tumor or the cancer applications, cancer therapy, the nanobots can also be used for breaking the kidney stones. These nanobots can carry a small ultrasound. So these nanobots will create some waves or ultrasonic signal generators are there. It will deliver the frequency directly to the kidney stones here. And you can see here the simple kidney stone can't pass through. The size is very large to pass through. So what happens is these nanobots can generate these shock waves, which can break the kidney stones into the pieces. Once it's broken, the smallest stones can pass through the urine. So nanobots can also be used for removing the fatty layer deposited on the arteries. Here, in the similar fashion as it crushed the kidney stones, it can also crush, or it can also clear the depositions on your skin or the blood vessel or the vein. And in future, we may also see nanobots in our mouthwashes. So we have this very trending or very popular advertisement wherein our popular actor Kajal comes out and asks, like, do you are salt or me paste lo uppunda, or your does your paste has salt in it? So why do you need salt, or why do we need other ingredients in our paste? Is to cleanse or to make our mouth or teeth not affected with the germs, or to prevent from eroding your enamel in the tooth, or it is helpful in alternate way for our tooth or mouth. So in future, uh, apart from biomedical applications, these nanobots can also be used for the day-to-day applications. So this is one similar example. Mouthwashes will have smart nanobots in future. So we can have these nanobots for cleaning the tooth here. So Nano is getting applications in all our day-to-day life also, and not confining only to the biomedical applications. And there are very important application here is the main problem with diagnosing cancer in the early stages is very difficult. So with the present tradition, uh, we can able to diagnose the cancer only in the later stages. Later stages is always after the third phase or the fourth phase. So there is an option of only going for radiation or chemotherapy in when you detect the cancer in the last stages. So by using nanotechnology, we can go for the early stage detection of a cancer, and we can protect the patient from the death of by cancer. And here the when you see when you see here the quantum dots, these quantum dots have optical properties uh, which depend greatly on its structure, particularly the color. Uh, this color will emit, uh, this color is emitted by the quantum dot, and this is dependent on the size or the diameter of the quantum dot. So you can see in this image here, there are various colors obtained by the quantum dots. So this color indicates the indirectly the size of the quantum dot. So if you can see here in this image, we have a cell, targeted cell structure by the quantum dot. Under the fluorescent microscope, if you see here, few cells are colored, like you can see pink or orange or green colored cells are observed. So this is because of the quantum dots which have been projected onto the affected cells. So this is how it works. The quantum dots here are not fluorescent when you apply the UV light, uh, uh, and when you apply the UV light, it emits some color. So by this unique principle of this quantum dots, we are able to map, or we are able to image the effective cells or organ in the body. So when you see here, the quantum dots are attached with some antibodies which go and bind to the cancer cells. So when the quantum dots bind into the cancer cell, and when you apply the light here, The cancer cell will only emit the fluorescence, and the healthy cells, there is no fluorescence observed. The pink cells are healthy cells, and the green ones are the affected cells, or you can call it as a cancer cells. So by this, only the cancer cells can be acquired, or cancer cells can be treated by keeping these healthy cells safe enough, and not to create any disturbances in the healthy cell. So this example gives how exactly the nanotechnology can be helpful in imaging or targeted drug delivery applications. And this is another unique application. Still, clinical trials are going on. uh, we have diabetic testings available in the market, which are of invasive. So you have to always prick your finger to uh, pick the blood from your body, and to test the glucose levels in your blood. So this is always a pain to a diabetic patient, to always prick your finger and always check the glucose levels. So here is one example of nano engineered glass, or nano engineered silica glass, with ions that fluorescence in infrared when low power laser hits them, and when the glass is in contact with the user's skin, the extent of fluorescent signal varies in relation to the concentration of the glucose in their body. So here the device measures the length of time the fluorescence lasts for, and uses that to calculate the glucose levels in the person's bloodstream. And without any needle and any process, uh, this process takes less than 30 seconds. So instead of pricking your finger, it is so simple. It acts like your biometric device. Just keep your finger on the device. Within 30 seconds, it will estimate the glucose levels in the body. So these nano engineered silica glasses, this research is going on in East University. And here is the article link I have provided. If you want to access to the article, you can. The next application here is again for the diabetic patients. Um, this sensor, this nanotechnology sensor, detects the uh, type A or type 1 diabetes in the breath of the person. So, acetone is usually found in a healthy person's breath, approximately 900 ppb. It is can be observed in a single person, but in the concentration will be doubled in the case of type 1 diabetic patient. So here they have used substrate with gold electrodes, or the gold electrode coating, with the ultra thin semiconductor film made of nanoparticles. And here in this tungsten oxide mixed with silicon is mainly used for the fabrication of nano sensor here. And in the presence of acetone, the electric resistance of the material drops. So this depends on the high electrical resistance. So by this, we can easily detect the diabetic person or non-diabetic person, by checking their breath concentration or acetone concentration. So this device works on electrical resistance. And this is another unique application where recently Google made a smart contact lens. So this contact lens have sensors, and this can detect a glucose in the tear. So this technology uses a small nanoparticles which is embedded into the hydrogel. So it is embedded into the hydrogel, wherein this can help in detecting the glucose levels in your tears. So these engineered nanoparticles react with the glucose molecules found in the tears, and it causes a chemical reaction that changes the color of the lenses. So you can physically also observe if the contact lens or the Google lens color, if it is changing, that resembles that there is some fluctuations in the glucose levels in the body. So this tiny lens will send the information about the glucose or blood glucose to the mobile phone also, and from there you can access the glucose level, and then keep an alert on your sugar levels in the body. So these are the main medical applications we have seen, and we'll now go to the energy applications, and I'll also focus on what work we are also performing in our laboratory. And so to give a gist about the energy applications, we have two categories of energy applications. One is energy harvesting, and second is energy storage. So our group is mainly focusing on the energy storage applications. So when we see here, energy harvesting can be categorized, or the applications are solar, hydrogen, nano generators, and other conventional energy. So our team is also focusing on the nano generators also. We have just entered into this area, and there are other stream is energy storage, where the vast research is going on electrochemical batteries, supercapacitors, hydrogen storage, and thermal energy storage. So our team is focusing on this supercapacitor applications. So here you can see the various one-dimensional, two-dimensional, and three-dimensional nanoparticles are playing a major role in triboelectric and supercapacitor batteries, superconductors, and nano lubricants as a smart windows, and nano refrigerants, as well as fuel cell, solar cell, and hydrogen generation, and vast applications are there using nanostructures. So here in future few slides, I'll be focusing mainly on how to design the material for your supercapacitor applications only. So just to give a brief idea of what exactly energy storage is, energy storage, it captures the energy, and then at one time the energy is being captured, and later you can use it for wherever you require. So it is like a power bank which you use for your laptops or for your cell phones. So basically energy storage is you can store the energy and then use it for your later time. So this device stores energy, generally is called as accumulator or a battery. So the power bank is also called as a battery basically. So this few technologies provide short-term energy storage, while others can provide a long time energy storage. So few examples here falls are supercapacitor batteries, thermal energy storage, and hydrogen storage. So in my future slides, in the to see with the research on the supercapacitor, I'll show how to design or how to prepare the nanostructures for supercapacitor applications. So coming to the first variety or the first category of energy storage is a battery. It is also called as electrochemical energy storage because it stores electricity at a chemical form. So that is why it is called as electrochemical energy storage. So the basic batteries, if you have to see in your daily life, is the primary battery mainly you see. So the primary battery examples here are the wall clock, the batteries which you use for a wall clock or a TV remote. Those are called the primary batteries. So basically, primary batteries are not usable, wherein secondary batteries are reusable. So those can be recharged and those can be repeatedly used till the shelf life or the life of a battery is sustained. So the examples here of secondary batteries are lithium-ion batteries or lead-acid batteries. And the batteries which we use in our car or vehicles, those can be charged again and can be used. So these fall under the secondary batteries. And basically batteries convert the chemical energy into the electrical energy. So basically electrochemical oxidation reduction reverse reactions happen between the material of anode and cathode. So this is the basic structure of a battery. Basically, it has an anode, it has a cathode and an anode, and it is separated by uh, material called a separator or an electrolyte. So this is the function of a lithium-ion battery basically. While it is charging, the electron moves from cathode to anode, and while it is discharging, electron moves from anode to cathode. So the basic nanomaterials where you can use for the battery applications are CNTs and tungsten silicate or tungsten silicate nanotubes, titanium silicate nanotubes, TiO2, titanium dioxide as an anode material. And as a cathode material, you can use vanadium oxide or lithium ferrites or lithium Mn or lithium cobalt as the cathode materials. Second category of energy storage here is a supercapacitor. Basically, our team is working on the supercapacitor here. This device is used to store extremely large amount of electrical charge here. So basically, we require large amount of electrical charge to use for a longer time. So instead of using a conventional dielectric, supercapacitor uses three mechanisms here, which is double layer, pseudo capacitance, as well as hybrid supercapacitor. So we are working on hybrid supercapacitor. Hybrid is nothing but a combination of one or two materials. So in future slides, we'll see what materials we are using in our research. And in these are the examples of the materials used in a supercapacitor. You can use carbon materials like graphene, CNTs, or graphene oxide, and you can have a compositions of graphene or magnesium oxide or ruthenium oxide. So you can have a mixture of materials also in supercapacitors. And the similar fashion of charging and discharging happens from when it have to charge the material, the electron moves from a cathode to anode, but when it is discharging, electrons move from anode to cathode. And this is the third category of hydrogen energy storage. In this, generally hydrogen can be stored in three forms: solid, liquid, and gas. But in this, we use nanomaterials like CNTs, metal organic frameworks, or graphite carbon nanofibers for the hydrogen storage purpose. And this is the fourth category, which is thermal energy storage. In this thermal energy storage, there are three steps. It can charge, store, and discharge with three storage cycle process. And the materials here also, you can use copper oxide, aluminum oxide, multi-wall CNTs, and graphite nano platelets. So when you see the research gap here, so here comes the basic research which we are performing in our laboratory. So here, if you see the research gap, we are trying to focus on the supercapacitor and comparing it with the lithium-ion battery. So basically, we work on the charge time, cycle life, and specific power and service life of the supercapacitor. So when you see the comparison, supercapacitor has very good properties, or can be beneficial for the recent applications. So, keeping in view these four functions, we wanted to overcome these four functions and make a better supercapacitor. So this is how the criteria we have developed in choosing the supercapacitor. Basically, we have a lot of materials where people are also working on: vanadium oxide, ruthenium, cobalt, nickel sulfide, nickel silicate, or MnO2. But we are mainly focusing on two main materials here, carbon and nickel oxide, because these are non-toxic. So our target is the toxicity, because toxic materials can affect the environment. So we wanted the environmental friendly materials to be used to develop a supercapacitor or an energy storage device. So these materials will have high cyclability, long-term stability. It has high specific surface area because we have carbon in it, and it is highly conductive, and it can have resistance to electrochemical oxidation reduction, and it has a high temperature stability also. So this is basic representation how we have prepared the material. We have taken nickel nitrate as a precursor material of nickel to prepare nickel oxide, and NaOH is used as a reducing agent, and we have made a composition of nickel oxide and reduced graphene oxide, and we made 0.02 weight percentage mixture of carbon in nickel. So we have used microwave assisted technique, because we have chosen this because it takes very less time for the preparation of the nanoparticles with a good yield of the material. So only 10 minutes time you take to prepare the nanoparticles here. So after preparing the nanoparticles, it is being calcined at 350 degrees centigrade to eliminate all the impurities, and ultimately the nanostructures are formed. And then further, to evaluate the nanostructures, we have performed X-ray diffraction and Raman spectroscopy, and we have confirmed the particle size, crystallite
Gentle
size.
reminder, Dr. Shilpa ma'am.
Yes, yes.
Yes, yeah,
Yeah,
thank
I'll wind off in maybe 2 minutes.
yeah, yeah, thank you.
So the average crystallite size and G band and D bands are observed using the Raman. And from scanning, we have got the flakes-like structures, and using EDAX, we have confirmed the composition. And when you come to the electrochemical behavior, this increased due to the nano size and high specific capacitance area of nanocomposite structures. So this current study we have done with two molarity of the electrolyte as KOH. And to wind off very quick, here if you observe the nickel oxide and RGO at 6 molar concentration of KOH is giving higher specific capacitance and having high energy density. So this is a basic prototype of flexible supercapacitor. Still testing and validations are going on this, and I would like to acknowledge DST Serve for R&D project funding. I also would like to thank DST Nanomission for supporting to start the master's program in nanotechnology, and also equip phase 3 and phase 2 infrastructures at Center for Nanoscience and Technology. And I also thank JNT University Registrar, Vice Chancellor, Rector, and Director, Institute of Science and Technology for complete cooperation in developing the center. And thank you.
Thank you so much, Dr. Shilpa ma'am. It was a wonderful talk ranging from various aspects of nanomaterials and very basics and to the applications from nano robots for various applications, from blood swimming robots for breaking kidney stones and for diagnosis of cancer and so many other applications. It was really a versatile and varied aspects we could discuss today through your talk. And there were many questions even from the participants. Some of them have posted in the chat session also for how do we prevent cancer, something like that. And maybe, yeah, that one question I will ask you because the other speaker is waiting. So one question was from Dr. Harika ma'am. She was asking like, how do we prevent cancer in the first stages if we know that? That was her question.
Okay. Okay. Prevention is nothing like to prevent in the first stage. We have to prevent not to get it to the first stage also. So try to prevent is how you have to maintain your lifestyle. You have to maintain your food culture and exercise, and these affect your body metabolism. So to prevent getting any kinds of disease or mainly on cancer, you try to mainly focus on your lifestyle, food habits, and exercise.
Yeah, one small thing, small correction in the sense like when you are explaining different four stages of cancer detection, you have introduced at one point that if we come to know about at this particular stage, through
Yes.
using these nano robots, we can prevent it. Like that was the discussion at that particular
Yes,
point.
yes. In
So
the
at
first
yes,
phase, you
yeah,
can identify the cancer, because at this stage of research, what medical field is doing is you can only identify cancer in your later stages, in your third stage or fourth stage only. But using quantum dots, when you use quantum dots as your therapeutic material, you can detect the cancer in very early stages, in the first stage or second stage, to get what do you say, you can avoid chemotherapy and radiation if you can identify it in the initial stages.
Vijayalakshmi madam. I'm sorry for disturbing you. Yeah,
No
please.
problem, no problem.
Yeah. Thank you so much, Dr. Shilpa. And actually, there might be just maybe I request other participants to ask one question. Maybe so whatever other questions you have, you can just you can send to Dr. Shilpa Chikra. I'll send her email and phone number. Or you can also redirect it to the organizer. So we will also redirect to her, and we will let you know the answers if any for that particular one. So, any questions from the participants? So I'm just unmuting all. Maybe if at all we can have one question. Thank you so much, Dr. Shilpa. Due to time lag, I couldn't give more time for the participants to ask question.
No
So,
problem. They can
yeah,
always mail me or contact me. I'm ready for
Madam,
that.
can I ask one question, madam? Madam.
yeah, yeah, please.
Yes, sir.
So, this is Professor Jaitan Reddy, Mechanical Department, Yoga
Yes,
University.
yes, sir.
Good morning, madam.
Good morning, sir.
Regarding nano robots, not to work anything, we require energy, right? How do
Yes.
you provide energy to the nano robots, which are
We have a
maybe,
supercapacitor or a capacitor built in the robot, sir. So which can help you to generate energy for the movement of the robot.
okay, if that maybe capacitor has lost the energy, then what will happen to the robot
So
inside the body?
it will be designed depending on the application, sir. So
Okay,
if you
okay.
require high energy, you have to use high
What,
energy storage of it.
what I meant to say is maybe it is inside the body. We
Yes.
don't know the reactions inside the body
So
due to some
that's why
reasons.
clinical studies are being made to
Okay, okay,
know how much energy is required to a nano robot for the metabolism or to move in the bloodstream to go and
okay,
access to the location.
okay. Right, thank you, madam. Great.
Thank you, sir.
Thank you so much, Dr. Shilpa ma'am. So maybe I'm sorry, due to time lag, I'm just ending the question answer session at this particular point. So I'll
No
surely
problem.
redirect all the questions to you, ma'am.
No
Thank you so
problem.
much for your excellent talk and thanks for accepting our invitation and joining us on the workshop. Thank you.
Honored. I'm honored to have as a speaker in this webinar, Dr. Mamta. Also thank Dr. M. V. Shankar sir also for inviting me, and thank you, Yogi Vemana University.
Thank you. Thank you, ma'am.
Thank
So
you.
I now welcome Professor N. Ramanohar Reddy sir to introduce our next speaker, Dr. K. Pratap from Hyderabad Central University. Sir, please share your screen, sir. So meanwhile, we will just introduce this.
Kaul, Assistant Professor, Center Advanced Studies in Electronic Science and Technology, School of Physics, University of Hyderabad. He had the research areas, lab on chip biosensors and magnetic sensors. Dr. Pratap Kaul has the research experience in the Central University Hyderabad and also University of Cambridge. He has the research experience in the Indian Institute of Technology, Bombay, and Tyndall National Institute, Ireland. He did his PhD in Material Science and Engineering in Changwon National University, South Korea, and also he did his in Electronics Flux Gate Magnetic Sensors, Andhra University, India. Dr. Pratap Kaur did his MSc Electronics with Physics, Andhra University, India. He did his BSc Mathematics, Physics, Electronics, C. YN College, Andhra University, India. For his credit, he has the 78 publications.
Yes.
78 publications, and it is very great opportunity to have his lecture at present occasion. Now I request Dr. Pratap Kaul to continue his lecture on this occasion.
Good morning, everyone. Am I audible?
Yes, sir. You are audible, sir.
Okay, so I thank the administration of the Yogi Vemana University and especially Dr. Mamata Kumari for inviting me to this lecture. So, in the current scenario, so conducting lectures on advanced materials for energy and environmental applications. So, is an apt one. And here I choose to give a different topic, like characterization of the materials. So in the characterization of materials, so there are many physical and chemical characterizations where SEM, XRD, TEM, UV visible and all these. So I choose to explain here about TGDTA and DSC. So the topic is an overview of TGDTA and DSC. So it helps us to clearly identify so what are the composite materials that are present in an alloy or a composite? What are the independent materials? So this is my research spectrum. I work on magnetic sensors, different types of magnetic sensors for navigation and biomedical applications. So I work on tuberculosis, cancer detection, and malaria detection sensors. And also I work on thin films, mostly magnetic thin films, and 2D materials. 2D materials means mixins, graphene, MOS2, etc. So 2D material and mixing 2D materials and metal nanocomposites for several applications. So most of them includes water purification, battery anode materials, supercapacitors, and multiferrites. So this is my research spectrum. And choosing away from my research spectrum, here I am giving the topic on TGDTA. So this is the equipment for TGDTA. You can keep your sample in this equipment and identify what are the elements that are present in your composite. either composite or a single material. So you could clearly identify what is present in it. So this is the most accurate measurement for knowing. So let us say that I am preparing a composite graphene cobalt ferrite. So how do I know that exactly graphene cobalt ferrite is formed? So how do I identify that whether there are any impurities in the material? So for this reason, so the simplest way we start with is XRD. So XRD has some limitations about graphenaceous components and other components. And you go for SEM EDAX or TEM EDAX. So they do have some particular limitations. And the other techniques that are employed for exactly knowing the each and every element that is present in the composite is AES. Generally, it is Auger electron spectroscopy or Auger electron spectroscopy. And this method is TGDTA. So in this method, we could exactly know what are the components, melting points, boiling points, and all this. So this is about, now we can have it as an interactive session. So now is everybody muted? Can you answer? So the first question here is, so what do everything have in common? Bread, chocolate, hair, fingernail clippings, ointments, explosives, kidney stones, everything. So if you are not muted, can you answer or can you type it? What do everything have in common? Any idea about it? So the most common thing was everything has a property while we expose them to the temperature, they will burn. So whatever is the material that is mentioned here or the materials that are available in this universe. So if you can supply sufficient amount of heat to it, definitely it will melt down. So that is the most important aspect of any material. That means that, so if you can heat the material, so you could know the signature of the material or the property of the material. So,
Sir, without melting also it will evaporation take place, na?
sorry?
Without melting also some materials will become vapor.
Yeah, they
What
can become vapor. Yes, they can become vapor, sir.
So you are telling all the materials will become liquid, that melting, na? That's what I'm telling.
Actually, I want to say that the materials change its phase, and change of phase is necessary in the thermal analysis. So either they will completely decompose or they'll change their phase. So that undergoing of changes is important to know the characteristics of the material. Okay. So the study of the effect of heat means it started long back. It's like man's early attempt to produce pottery, extracting of materials, making glasses, so examining of minerals. So it started long back in what do we say, before Christ regions. So early human being knows that. So if a material is treated with heat, so it will undergo some changes. So he can make something using that. So here we are trying to use the same thing when we supply heat to a certain material. It will undergo some important changes, and those important changes are being recorded or analyzed. So this is the brief summary. Everybody knows it. When you heat in material, so it's like heat is transferred from one form to the other form. So that transfer requires temperature difference, and it is done in either conduction, convection, or radiation. So the laws of thermodynamics deals with so either means zeroth law or first law or second law. So they play an important role in these thermal analysis. So to provide useful qualitative and quantitative information so about the heat of the materials, so experiments should be carefully planned, and often it should be made with sophisticated equipment. So in the beginning, we have discussed that if we heat the material, it will go some interesting changes, undergo some interesting changes, and those can be analyzed. So means it is dangerous to subject any material to such heat and to observe it directly. That means that so you lit up a fire, throw some material into it, and observing it. Some materials might be really dangerous. So for that purpose, so we are saying that we need some sophisticated equipment, and the experiment should be carefully planned, not like a material is thrown into the fire and observe what it happened. So it should be having proper ambience, means either in air vacuum, air ambience or nitrogen ambience or whatever it may be. Heating should be done in proper ambience, and heating rate should be controlled, everything. Okay, I'll go through it next one. So these are the definitions of thermal analysis. So the older definitions, there is a council called as ICTAC, and that ICTAC governs all the laws, whatever it may be, for thermal analysis. So they have given a newer definition compared to the older definition. So older definition is like, so it refers to a group of techniques in which property of a sample is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed. And what the newer definition says is, so it is change in the property of the sample which is related to an temperature alteration. So these are the two definitions. And what exactly the newer definition means. So in the newer definition, it is saying that analysis means that it is not only just observing. Analysis means that so recording the data at each and every point and its meaningful interpretation. So monitoring means that only just looking into it and observing what is happening. So that is about the newer definition. And in the newer definition, the word analysis is added, and it is aptly supported that the newer definition is really appropriate for thermal analysis. So temperature alteration. So temperature alteration means that so how do you change the temperature while you are testing your sample? So it can't be random temperature, like first of all I'll start with 0, then I'll go for 500, again I'll come back to 100, then I'll go to 2000. So after that I'll do it randomly. So it is like it can't be done in that way, no random alterations of the temperature. So a stepwise change from one constant temperature to the other constant temperature. So stepwise change means, so first of all I'll give 5 degrees, then I'll increase +5, +5, +5, something like that. So actually it doesn't start with 5 degrees. Normally all these thermal analysis starts with room temperature. So we call it as 30 degrees or 30 degrees. So 30 plus 5, 35 plus 5, 40 plus 5. So it depends on how you want to analyze your sample. So the step size depends on how you want to analyze your sample. So linear rate of change of temperature, this is the other one. And modulation of constant or linearly changing temperature with frequency and amplitude. So controlled heating or cooling. So controlled heating or cooling means, so let us say that if you are heating a sample in the open atmosphere, so the atmosphere might interpret the burning of the sample. So if the burning of the sample is happening in a very cold area, so due to its surrounding atmosphere, the cold weather might influence the heating of the sample. So let us say that if it is taking up in a hot area, so it will affect it. So a controlled atmosphere means we'll have a closed chamber in which you are heating your sample and the outside atmospheric temperature variations can be ignored. So that is called as controlled heating or cooling. So even for every definition and every word in the definition, they have clearly given what exactly it means. So here, thermal and let me read it out. Thermal analysis is a group of techniques that study the relationship between sample property and its temperature. So here, so this is the given definition by ICTAC, and so they have also defined that what does a group means and what is a technique means and study and all these relationship, sample and property. Why? Because so group means I can define one definition saying that a group means these three are group, and you can define one definition for a group. So irrespective of a person, ICTAC has defined a group definition, and they have defined a definition for techniques. So this one and all these. So and study. What does study means, and what is relationship means? What is sample means? What is property means? What does temperature means? Here, it's like group means that thermal analysis comprises of a diverse range of techniques and experimental types considered means they are collectively if total measurement conforms to the definition. So techniques means so a technique is how do we say it? A technique is characterized by so what is the method you are using for the sample that is to be under investigation. So that is how you call it as a technique. And what are the other definitions? So study means that how do I erase it? Okay. Give me a minute. I'm trying to erase them. So what does study means? So study implies that it is an integral part of thermal analysis, and so it is like interpretation and discussion of the measured data. Interpretation and discussion. So relationship. So relationship means that so as a function of temperature. So this is what they are saying. As a function of temperature. And sample. Obviously, everybody knows that sample means what is the material you want to study is called as sample. And property means that so it is the either physical or chemical property of the sample. So temperature you already know. So it's like so how do you increase or decrease it? So okay then So these are the wide properties are means this table gives us what is the property and what is a technique and how do we analyze it for thermal analysis. So what are the properties that are studied? So if you study heat, and the technique is called as calorimetry. So if you study the property temperature, so you call that property as thermometry. So sometimes it may be called as heating or cooling curves. So, and if you study temperature difference, so you call it as differential thermal analysis. So the abbreviation for it is DTA. So here temperature difference is determined between sample and a reference material. So here the other one is heat flow rate. So how much heat is flowing for particular amount of time. So if you are studying this property of heat flow rate, so the technique what we use is called as differential scanning calorimetry. So it is also called as DSC, and so heat flow rate is between the reference material and the sample. So if you are analyzing mass, means the change in mass while you are heating, so you call that technique as thermogravimetry, TG, or thermogravimetric analysis, TGA. So you are observing the change in mass of the sample while heat is being given to the sample. So there are also other techniques called as dimensional and mechanical properties. Means if you are analyzing dimensional properties, dimensional means so we have given a rod of sample, and if it increases its length or decreases its length. So okay, let me. So if it is dimensional and mechanical, so it can be dynamic mechanical analysis, thermomechanical analysis, and thermodilatometry. So dynamic mechanical analysis is called as DMA. Thermomechanical analysis is called as TMA, and it is thermodilatometry is called as TD. In dynamic mechanical analysis, modulus is determined or moduli is determined. In thermomechanical analysis, deformations are measured. So did the sample deform to another shape? In thermodilatometry, dimensions are used, means whether the sample has increased its length or decreased its length. So these are the properties studied by thermal analysis. Okay. So why do we use thermal analysis? So why do we use thermal analysis means so to measure the property of interest such as specific heat, latent heat, heat of reaction, to fingerprint a particular material of a substance. So this is where mostly material scientists use thermal analysis like TGA or DTA to access high temperature stability of materials, to detect phase transformations, fundamental studies of kinetic reactions. So my part mainly concentrates on DTA, DSC, and TGA. So these are the basic principles here that are shown. So DSC, differential scanning calorimetry. So it means that so heat flow rate is being measured. So look at here, the heat is flowing and rate of flow of heat is measured, and the graph of DSC looks like this. So TS minus TR means temperature of the sample minus reference temperature is equal to 0 versus T. So differential scanning calorimetry, RDTA. So reverse differential thermal analysis. So dT by dt versus T. So RDTA means, so look at the graph here, and thermal analysis. Thermal analysis means the temperature of the sample versus the applied temperature. So this is how the graph will be. I'll explain these graphs in the next slides. So thermogravimetric analysis, it means that change in mass of the sample with respect to the temperature. TTA. So change in temperature with respect to the reference temperature. So these are the techniques, and so differential analysis. So I think I'll move a little bit faster. So differential thermal analysis involves heating or cooling of a test sample, so which is under reference under identical conditions. So the difference temperature is plotted with respect to the time or against temperature. So means the definition says that so a technique for recording the difference in temperature between substance and reference material means so in your equipment there will be a reference material and there is a substance. So the difference between these two temperatures with respect to time or with respect to temperature. So this is how DTA graphs will be. So here the dotted line is furnace temperature, and this is the temperature of the material which we have kept in the equipment for analysis. So the drop here says that the material is melting, and so the position at which it is coming, it is not significant. Only thing was, so where is the melting point coming? So this is about DTA scans and TA scans, and it is DTA. DTA means change in temperature delta T with respect to the reference temperature. So this is the melting point, and at the melting point there is a dip in the curve. It means that it is an endothermic reaction, means that heat is absorbed while the material is melting. Hence the temperature change is negative here. So this is how DTA scan will be, and this is how DTA apparatus will be. So apparatus means so here is the reference material, this is the sample, and this is the chamber in which our sample is placed. So these are the two thermocouples, one thermocouple and the second thermocouple for measuring the temperatures. So these thermocouples measure our sample and reference thing. So this is the heating coil. So this heating coil increases the temperature in the furnace. So here there is a gas inlet. So whether you want to do in which ambience, so you want to do in nitrogen ambience or argon ambience. So it depends. Okay. So DTA. Yes, please. Someone is talking. Hello. Okay, I'm continuing. So the reference material. So how do you choose a reference material? So it should not undergo thermal events over operating temperature. It should not react with sample holder, and both thermal conductivity and heat capacity of the reference should be similar to that of the sample. Okay, and then so differential scanning calorimetry. So differential scanning calorimetry. So this is how our equipment looks like. So this is the reference material, and this is the sample. So heat is flowing through this tube. We can say that this is the tube where heat is flowing, and there is temperature sensor for reference, and there is temperature sensor for the sample. So here it is like the entire chamber is not being heated. Here only there is a flow of heat. So flow of heat means, so it can be hot air or anything. So there is flow of heat, and our sample is being heated, such that it undergoes property changes. So where DSC is used, differential scanning calorimetry is used for measuring melting temperature, heat of fusion, latent heat of melting, reaction energy and temperatures, glass transition temperatures, crystalline phase temperatures and energy, precipitation energy and temperature, denaturation temperatures, oxidation index and times, and all these. So for DSC, there is a limitation. Only non-corrosive samples can be analyzed. So no organic and other materials containing fluorine, chlorine, bromine, iodine may be submitted for DSC analysis. So I'll skip this part. So I'll go to these different parts of differential scanning calorimetry principles. So there are two different types of, I think 2 or 3 different types of DSCs. So one is called as a power compensation DSC, and the other one is heat varying in DSC. So let me go here. So heat flux DXC. So look at here. This is the power compensated DSC. Power compensated DST means, so here is our sample, here is our reference, and there are independent chambers and independent heaters. So, but they analyze our sample. Single heat source DSC. Single heat source means, so this is a chamber. In the chamber, there is the sample and the reference, and you are heating them with a single source, and you are observing the change in temperature delta T. So this is about single source DSC. So where is this heat flux DXC used? So actually we took an example of DuPont GSC by Baxter and Greener. So the system is a subtle modification of DTA, differing only the fact that sample and reference crucibles are linked by a good heat flow path. So the difference in energy is required to maintain them at a nearly identical temperature. So modern DTA equipments, the thermocouples are not embedded in either the specimens, so they are separate. So the fact that temperature difference is small, it is important to ensure that both containers are exposed to essentially same temperatures. So it means different chambers for each and everything should be a good idea. So when you measure DSC, so there are 3 components that should be measured or that should be monitored. So one is gradient, baseline, and calibration. So why? Because when you measure any graph or any material using DSC, you will get a data. And for that data, corrections are always required. So how do you correct baseline? So linear baseline, sigmoidal baseline, and tangential area are proportional baseline. So this linear baseline is used for measurements in which there is no significant change in CP. Okay, the linear baseline is generally used. So when there is no significant change in the melting. So the other one is the sigmoidal baseline. So in the sigmoidal baseline, so it is used when melting process is accompanied by a notable change, means significant change in the CP. So tangential area proportional to the baseline. So this is how the graph will be. So I'll show it in the next one. So this baseline is used when melting process is accompanied by notable CP change and a sloping baseline exists. So I'll show some examples in the next one. So look at here. So this is the sigmoidal baseline. So I think you remember that when is sigmoidal baseline used? So when it is accompanied by notable change in the CP. So when there is change in the CP. So the other one is linear baseline. So linear baseline is used when a simple melting process is involved and CP is very less. So look at the baseline here, it is linear. And tangential or area baseline. So tangential or area baseline so is used, look at here. So it is used when melting process is accompanied by notable CP. So and also sloping baseline exists. So look at here, there is a change in the baseline at this level and at this level. So when there is sloping baseline. So these are the baseline corrections. So okay. So these are the temperature on the peak point does not correspond to the melting temperature. So look at here. So it does not correspond to the melting temperature. So after peak maximum, the signal diminishes slowly. So how do we correct it? So correction on thermal resistance between sample and DTA. So if it is a bad thermal contact, the melting time will be melting time will be long, and the peak will be broad, and it will have less intensity peak. So something like that. So the time will be long, and peak will be really broad, and it will have less intensity or less height. So if it is a good thermal contact, the peak will look like this. A sharp peak with very good intensity, high intensity or amplitude, and the time is very less. So here the slope of the left peak is dependent on the thermal resistance, peak area, and it equals the melting impact. So look at the other other correction. It is time constant. So this is consumed heat, the red one. This is measured signal when time constant is small. So this is measured signal when time constant is very large. So how do you correct it? So how do you correct it means that so measured signal is equal to integral of 0 to t. So consumed heat into g of t. So it is a exponential function of temperature by time constant. So you look at graph in the next slide. So look at it here. So the original signal is the red one. After measuring a DSC, the original signal is the red one. And this one, the lavender color one, is corrected for time constant. And this is corrected for thermal contact also, blue one. So now look at the graph. So the melting point is somewhere around 157, but we got it as 159. So corrections are necessary for DSC. So in DSC, there are several noises, we can say, or misleading things that will come. So in exothermic reaction, if you observe a graph or curve like this, so you can identify that the sample is moving in the pan. And if you observe a peak like this, it can't be called as peak. If you observe a curve like this or something, a spike like this, sample pan is disturbing. So sample pan is moving in the distance. So if you observe a curve like this, it means that there is mechanical shock or we have pushed the bench. So if you observe this picture sort of thing means a graph in this method. So we can identify that cool air is entering into the furnace. So this doesn't mean that it is any signal or an important information about the sample. So these are all our unwanted signals that are happening due to sample movement, fan movement, mechanical shock, and cool air entry. So in endothermic reactions, it is, if a spike occurs like this, it is electrical effects, these two, and when there is change in atmosphere, there is an increase in it. And if pan lid is broken or it is burst, so you will get a spike like this. And so closing and opening pan, if there is a hole, so you'll get a graph like this. Okay. So these are the applications of DSC, metal ion melting, magnetic structures, heat transformations, oxidation temperatures, exothermal energies, melting points, and all these. So I think I'll run a little bit faster. So now please inform me when before 5 minutes of my time, okay? Thermogravimetric analysis. So this technique uses mass, means the change in mass. Mass of the substance is measured as a function of temperature, while the substance is subjected to controlled temperature program. So this is how the apparatus looks like. So a furnace, sample, and there is a microbalance. Microbalance means used to measure the mass. Why? Because so as we are heating the sample, so we are expecting to change the mass of the sample. So we have a thermobalance. So here thermobalance is a combination of suitable electronic microbalance with a furnace, temperature programmer, computer control that allows the sample to be continuously weighed and heated or cooled in a controlled manner. Okay, so this is how the mechanism of thermobalance looks like. Here, the weight of the sample is continuously monitored. So,
Dr. Pratap, sir.
yeah, please.
Gentle reminder, sir.
Okay, I'll wind it up. I'll end it up. Okay.
Yeah, yes, sir.
Okay. So, whatever samples we are measuring here are solids. So, how does a TGA graph looks like? So, this is y-axis is mass, x-axis is temperature. TGA looks like this. Means once you start heating the sample, so let us imagine that it is a composite. First composite melts. First element is melted. So this is the signature that one element in the composite has melted. And this is a significance that second element has melted. And this is third element has melted. So from this graph, we can say that it is a 3-element composite and one element has melting point around at maybe 250, other one at 500, maybe the other one around at 700. So if you make a differential of this curve, so it is DTG. Okay, so thermogravimetric analysis depends on the change of mass, means initial mass and final mass. So I'll end it up after explaining this one. So these are the different types of curves you see in thermal analysis. So type 1. So there is no mass change over the entire temperature. So it means that so you need to check what is the sample you have given for the measurement. So the material could be heat resistant. So type 2. So this is type 2 and there is a rapid mass loss. Means it might be a liquid and it have dried up initially. And what is that one? The third one. So it is decomposition of a sample in single stage. So whatever sample you have given, so it has decomposed in a single stage. The third one. And the fourth one. So it indicates multi-stage decomposition of the sample. It means that 1, 2, 3. There are 3 different elements in that sample. So sample 5. So it also represents multi-stage, but there are no stable intermediaries. So it means that so you need to check the effect of heating rate or resolution. So you need to check how does did I give a proper heating rate or not. And type 6 curves. So where is our type 6 curves? So this is an abnormal phenomenon where it is showing gain in the mass. Means giving the sample for measurement, it is gaining the mass. So I think that oxidation might have happened. And type 7 curves. So obviously you don't come across these ones, but it is like it is oxidation and the sample has decomposed again. So whenever you are getting TGA graphs, analyze under which category your graph is falling and try to interpret your sample accordingly. Okay, maybe, so this is about a polystyrene sample I took. And so first of all, styrene and fiberglass means it has decomposed in 3 steps. I think I'm ending it up here. So what are the uses of TGA? So it determines the temperature and weight change in the composition reactions, and it allows reactions with air, oxygen, and other reactive gases. Can be used to measure evaporation rates as a function of temperature. So allows to determine Curie temperatures, magnetic transitions by measuring temperatures. So helps to identify plastic and organic materials by measuring temperature of food things. So one example is that food adulteration can be identified by this technique. So let us say that we took our food is given for TGA analysis. So everything should decompose at one temperature. So if they are plastics or any other materials, they will give a different peak. Okay. So this can be used for food adulteration also. So use it to measure the weight of fiberglass, inorganic films, and also. So it can be okay. That is what it is written here to check the quality of the foods, distinguish between the mineral composites. So acknowledgements to my professors, and so these are some of our papers. So these are the additional resources about TGA or anything if you want to check it out. And thank you.
Thank you so much, sir. It was an excellent talk on different ways of analyzing TGDTA. And now I request the participants, if you have any questions, you can interact with the sir. You can unmute yourself now and can ask sir.
Sir, good morning, sir.
Good morning.
Sir, this is Shankar from Yogi Vamana University, sir.
Yes,
Thanks for
please.
your excellent talk on thermal analysis, TG and DTA. It was really, we have learned some more fundamentals and important interpretation as well.
Yes, sir, please say.
So we often get one doubt, sir, regarding the material. We have prepared the materials using surfactants.
Okay.
So we have to eliminate the surfactant by heating, by doing calcination at a suitable temperature, sir.
Okay.
Maybe 350 or 400, depends upon the surfactant.
Okay.
So do you have any suggestion to identify the suitable temperature, sir, using this TGDT?
No, I think that if you can subject this material to the TGA, so you could know the exact boiling point of it. means when does it evaporate? Maybe exactly, I'm not sure whether your surfactants can be given to the TGA or not. But
Okay, sir.
so please take the suggestion of that TGA operator whether this material can be given or not, and then
Okay.
try to check. So what is the evaporation temperature of it? Means phase change of it. So then I think you could exactly get what is the temperature, and you could use that temperature for calcination, I guess. But
Okay,
check
sir.
that that calcination temperature should not merge with the material temperatures.
Yes, sir. Yes, sir. I understand, sir. So
Oh.
we have to be cautious in selecting this temperature.
Yeah, temperatures.
I
Why?
understand.
Because you should not meet any of the material properties of these materials. Because whatever fundamental material we are having,
Yes, sir.
and that material should not react with our calcination temperature.
Okay, sir.
Mm.
I do understand, sir.
Mm.
Thank you, sir. Thanks for your nice explanation, sir.
Thank you very much, sir.
Thank you, Dr. Pratap. I have a small query. So
Yes, please.
we do have enthalpy change during the TGA process. So
Yes, sir.
now whether will there be any effect in the heat capacity of the material during this heat treatment of the process?
No, mostly no, because enthalpy plays an important role here. Mostly it won't affect the heat treatment.
Heat capacity of the material. Okay.
No, CP won't be changed.
Okay. So thank you so much, Pratap sir. It's really great to have you on our workshop, and thanks a lot for your excellent cooperation to be here. Thank you.
Thank you
So
very much. Thank you.
any participants, if you have any questions, you can, I will send the Pratap sir's mail ID in the group, WhatsApp group. You
This
can,
is Subramanian from Bangalore. I have one question.
Yes, sir, please.
My area is thermoelectric material. So
Okay.
thermoelectric material, thermal energy converting to electricity.
Okay.
So in my sample, I want to find out how much heat is passed from one side to the other side.
Sir, there is some noise coming from the background. Could you please check it out?
So
Okay. Otherwise, could you please type? Because I'm getting some noise, sir.
yeah, there is some noise, yes. Sir, you can still pose your question in the chat box, sir. I will direct it to sir. Hello, Subramaniam sir. Okay. Yes, sir. Thank you, sir. Thank you for asking question. Yeah. Sir, Pratap sir,
Yes, please.
thank you so much. Maybe we can have another sessions of this kind in next time in offline also. So we
Yes,
would
sir.
welcome you to our university next time, sir. Yes,
Okay,
thank you
please.
so much. Thank you so much, sir. Thank you.
We are eagerly waiting for traveling.
Yes, 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 sir. Yes.
Okay. Thank you for the
Thank,
invitation. Thank you very much.
yes, thank you, sir.
Mm.
All the participant now, I request you to be online. We have the next session with the next invited speaker. Can you just be online for 1 minute? We are introducing the new speakers. Please be online. So now I invite my colleague, Professor M.V. Shankar sir, to introduce our next speaker.
Good afternoon, all the participants. It is indeed a great pleasure to introduce Professor R.P. Vijayalakshmi Madam in a department from a Department of Physics, Sri Venkateshwara University, Tirupati. So, Madam has the Department of Material Science and Nanotechnology and the university having a lot of communication with the Department of Physics of SV University, that is our parent university originally. And the Department of Physics has contributed much to our department. So, coming to Madam, Madam has a very good teaching experience for more than 22 years. And Madam serving as a professor the last 7 years in the Sri Venkateshwara University, Tirupati. Madam has published more than 98 papers in international peer-reviewed journals. And Madam's credit, more than 15 students are graduated for PhD and 3 MPhil students. Besides, Madam is very amicable and friendly for the students as well as all the faculty members in their own department as well as in UBM University as well. So, with this brief introduction, we invite the Madam Professor R.P. Vijayalakshmi Garu to deliver it.
Hello, is it audible, sir? Is it audible?
Yes, Madam. Yes, Madam. Yes,
Okay.
Madam.
Okay, sir.
Please, Madam. Please continue.
Okay. Good afternoon to all of you. It is great pleasure for me to thank the organizers of the Yogavemna University and my sincere thanks to Professor M.V. Shankar Garu and Dr. M. Amita Kumari for inviting me to deliver lecture on this workshop. So I am going to speak on cost-effective methods to synthesize the nanomaterials. So those techniques what we have used to synthesize the nanomaterials in our laboratory. This lecture is mostly useful for students or scholars, those who are going to do research in terms of the nanostructures. So this is mostly useful for beginners, those who are fascinated to work in the field of nanostructures. So this is the outline of the lecture. So I am going to give the brief introduction. What are the techniques that are available in terms of the nanostructures and how to grow nanostructure in terms of the cost-effective methods, and what is the summary of the different methods that are used to grow the nanostructures. So this is the outline of my lecture. So in the case of the device, when you want to form the device in terms of the materials, so what you require is you require a material with new physical properties and with applications. So to get a material with new physical properties and applications, what we have to do is we have to synthesize the material with desired shape, size and morphology and crystal structure with chemical composition. So then only we can use that material for particular device applications. So because of this reason, the synthesis is playing very important role to use the material in terms of the device applications. So the synthesis process is very important to get the material with new properties. This is a thing that is to be noted. So next one, so when you take in terms of the particular synthesis materials, so here when you classify broadly, so we can classify the synthesis materials in terms of the classification. So we have the two approaches. We can take those approaches as the top-down approach and the bottom-up approach. So these are the two approaches that can be used to synthesize the nanostructures. So when you see in terms of the top-down approach, so when you take in terms of the top-down approach, in this one, we have the bulk material. So that bulk material is ruined into small structure. Finally, you will get a desired shape and size. So that is the top-down method. So in the case of the top-down method, what we will do is we will take the bulk material. So we have the so many techniques to ruin down the structure. By ruin down the particular bulk material, you will get a desired structure. So what is the thing we are doing is in this one, in the case of the top-down method, So to get the desired structure, we are doing the bulk material, then only it is possible to get the desired structure. So what are the methods that can be used to ruin the structure? Means we can use the different techniques. That is, one is the ball milling, sputtering, nanolithography, laser ablation, physical vapor deposition, etching, cutting. So these are the a few methods that can be used in terms of the top-down method. So in this one, the basic thing is we have to ruin down the structure. As soon as when you ruin down the structure, so in this one, there is a possibility to formation of the more number of defects, and the crystal structure of the particular material is also getting damaged. So that is the major problem in terms of the top-down method. So as soon as the top-down method is considered, so we have the more number of defects, and with crystal damage, there is no possibility for the uniform structures also. So there is a major drawback in terms of the top-down method. In the case of the top-down method, mostly the methods in terms of the top-down method are the physical methods. So in this one, what is the advantage means you can get a huge quantity of material. So that is the advantage in terms of the top-down method. So next one, we can take the other advantage method. So that is in terms of the bottom-up method. So in the case of the bottom-up method, what you can do is we can grow the structure by depositing atom by atom, molecule by molecule. So by depositing atom by atom and molecule by molecule, what you can do is we can get the required structure and shape depending upon your requirement to use that one in terms of the device application. So this is like this. When you have the bricks, what you can do is, so when you want to build a house with such a particular structure, so what we have to do is we have to place the brick, placing the brick in a design. So by one, what we will get is you will get a house with a desired structure. So the same is the case in the case of the nano materials growth also. What you can do is instead of the bricks, what you can do is we can use the atoms or the molecules. So when you place the molecules or the atoms, by depending upon your requirement, you will get a required structure. So what are the material, what are the methods that can be used to get the required actual structures is we can go for the co-precipitation method and the colloid method, hydrothermal method. We have the micro emulsion, sol gel, electrodeposition. So these are the a few methods that I have mentioned here. So we can use all these methods to get the nano structures depending upon requirement to use those materials in terms of the different applications. So in this one, this actually what is the drawback in this method is it is a long process. So we have the choose the compatible surfaces and molecules. So what is the advantage in this method is, so this is a very good method. This is a very good approach. In this one, we have a material with low number of defects and with good uniformity and good composition. So that these bottom-up methods, we can use this method to get a material with the required size and dimension. So when you take in terms of the top-down method and in terms of the bottom-up method, so the bottom-up methods are suitable to get the nanostructures in terms of the design, shape, and size. So next one, so what are the methods which I am going to cover in this lecture is, so I am going to cover about the chemical vapor deposition, hydrothermal and the solvothermal synthesis and sol gel processing, CVD. So these are the methods which I am going to cover in this lecture. So why I have chosen all these methods means all these methods are very cost effective and we can get good nanostructures by using this one. So those who are in the beginning of the fascinating towards the nanomaterials, they can go through these methods so that they can get a variety of nanostructures by using with less expenses. So that I chosen these materials. These materials are in terms of the cost-effective methods. So when you take in terms of the chemical co-precipitation method, so what is the advantage in terms of the chemical co-precipitation method is, it is very simple and inexpensive. It is, we can control the size. It is easy to maintain the stoichiometry, and the materials that we are going to use to synthesize this material is, it is very less expensive. You can, those are easily available also, and there is no need to go for the sophisticated instruments and the equipment. So there is no chance of coalescence in terms of the solid form or in terms of the liquid form. So these are the mostly main advantages in terms of the chemical co-precipitation method. So this method is suitable for to get variety of nano particles, to use these particles for many number of applications. So this method is very less expensive method, so that when you want to grow the nano particles, we can go for the chemical co-precipitation method. So in this one, what is the actual apparatus that is required to grow the nanoparticles in terms of the chemical co-precipitation method are? So we have these four things we require to grow. So all these things are less expensive. It will cost less than 1 lakh only. In this one, we have the burette to pour the liquid into the required amount. So we have the actual magnetic stirrer and magnetic pellets, and this is the waffle furnace what we have to use to anneal the material after synthesis. So these are the four things that we require in terms of the chemical co-precipitation method is concerned. So in this one, so when you take in terms of when you go for the chemical co-precipitation method, so when you have the reaction, so while the reaction is taking place, so we have the nucleation. In the nucleation, the growth process takes place. As soon as the growth process takes place, so the growth process takes place in all directions. When the growth process takes place in all directions, so there is a possibility to grow the crystal in. It is not possible to grow the crystal with the required size and shape, so it will grow in all directions. So that to control the growth of a particular particle while growing, what we have to do is we have to use the capping agent, stabilizing agent, and the dispersing agent. So dispersing agent meant to solve for solubility, we will use the dispersing agent. So we have the capping agent and the stabilizing agent. So these two terms are using side by side, but the capping agent is the actually how the capping agent works means, so as soon as the nucleation starts, we have the growth. As soon as the growth starts, so we have to control the size of the particle. So we have to avoid the growth in all directions. So that what we will do is we will use the capping agent. In the case of the capping agent, mostly these are in terms of the polymers or organic materials. In that one, we have the steric effect is there. This steric effect controls the growth of the particle in all directions. So like that, the capping agent controls the growth of a particle in all directions. So by using the capping agent, what you can do is you can get a nano particle with the required size and dimension by using the capping agent. So what is actually the action of the stabilizing agent? So we have the stabilizing agent. So we can use actually we have the PEG polyethylene glycol that can be act as a capping agent and the stabilizing agent and the dispersing agent also. So in some organic materials they act only for the particular purpose only. So depending upon the material what we are going to synthesis, so we have to choose the capping agent and the stabilizing agent depending upon your requirement in the which material we are going. So what the action of the stabilizing agent here is, when you have the stabilizing agent, so in this one, it controls the agglomeration of the particle. As soon as the growth of the particle is taking place, so we can control the growth to get to the required side by using the capping agent. So when you have the so many particles are together, there is a possibility for joining of the particles with some attraction. So what we have to do is we have to use the stability agent to avoid the agglomeration of particle one to other. So like that, as soon as when you go for the synthesis in terms of the chemical co-precipitation method, so we can dissolve the material depending upon the particular actual material what you are using. You can dissolve that one in terms of the acid or in terms of the base or in terms of the acid, water. So we have to maintain the correct pH to get the actually the pH, temperature, and all these things are playing very important role to actually to get it reacted. After reaction only you will get the actual what is a compound you are going to get. So that to take place the reaction, what we have to do is we have to maintain all these things. In addition to that one, we have to add the capping agent and the stabilizing agent also to get the nanoparticles and in required dimension and shape. So that the capping agent and stabilizing agent are also very important in the case of the chemical co-precipitation method to get the nanoparticles in terms of the apparent shape and size. So next one, so this is the some actually the flow chart. So in our laboratory, So we are doing, we did lot of research in terms of by using the chemical co-precipitation method. We use the chemical co-precipitation method, and we use the chemistry. So all these methods we already we are doing the research in the same the methods only. So in this one, when you take the cadmium sulfate, here we synthesize the cadmium sulfate by using the different capping agent. So to see how the capping agents will work on the actually the size of the particle. So to study that effect, we have used the different capping agents to synthesize the cadmium sulfate nanoparticles. So to synthesize the cadmium sulfate nanoparticles, here the actually the raw materials required what we had taken to synthesize in our laboratory is we took the cadmium source as a cadmium acetate and for the sulfur source as a sodium sulfate. So in this one, we dissolve that one in terms of the deionization because the cadmium acetate is easily soluble in water. So that we dissolve that one in terms of the actual deionized water. Then we have the two solutions. We combine this one in terms of the required stoichiometry mainly. We fix the molarity. So by fixing the molarity, so we prepare the two solutions. After preparing the two solutions, we stir that one for 30 minutes. Then we have added three capping agents. So here we have the three capping agents: polyethylene glycol, EDTA, polyvinyl pyrrolidine. So these are the three capping agents we have used to synthesize the cadmium sulfate nanoparticles. So this is the just simple synthesis process how you can get the cadmium sulfate nanoparticles by using the different capping agents. So in this one we can see, so this is the actually the graphical abstract. So what we can use to synthesize the actual nanoparticles in terms of the cadmium sulfate. So we have the, this is the cadmium acetate and this is the sodium sulfate. So we have dissolved that one, we have the final liquid. So then if there is a magnetic stirrer, we stir it that one for some, what is the time, 8 hours. Then we have the reaction, then we got the actual precipitation, then we filtered, then it was calcinated. So to avoid the actual, to get the homogeneity and to remove the water that is present in the particular material. So we calcinated, we heated the material at 80 degrees centigrade. Finally, we obtained the cadmium sulfide powder. So like this, we can get the variety of powders also by using the precipitation method. So this is also one of the good method to synthesize nano particles in terms of the actually the nano materials is concerned. So in this one, so as I mentioned earlier in the earlier set, so we synthesize the cadmium sulfate by using the three capping agents. So only to study what is the effect of the capping agents on the particle size. So when you observe the same micrographs in terms of the actual three capping agents, so when you see this one, this is the cadmium sulfate without any capping agent. So this is the cadmium sulfate nanoparticles with the PEG capping agent, and this is the cadmium sulfide in terms of the EDTA, and this is the cadmium sulfide in terms of the PVP. So when you observe all these some micrographs, so what you can observe here is, so this is the cadmium sulfide, it is prepared without any capping agent. Here the particles are agglomerated, we have the, so all the particles are very big in nature. So in this one we have the PEG cap nanoparticles, in this one the particles are small, so this is like this. So when you observe EDTA, so this is also the particles are big. So when you see in the case of the PVP, this is, so that means when you observe all these four diagrams as per the same morphology is concerned. So in this one, we can see the PEG is a good capping agent that is suitable in terms of the cadmium sulfate. So that means we have to check the by trial and error procedure which capping agent is suitable to our material to get the particles in terms of the desired shade and shape. So like this, we can see by using the trial and error procedure, all these materials that were used are less scarce, so that we can try it for many times which capping agent we can use to get the actually the required materials with required dimension and shape. So like this, we can grow the variety of the nanoparticles by using the different agents. So because the capping agent means we have the much agglomeration, so that it is not possible to get the with required shape and size. So this is another flowchart that is showing. So usually in our lab we have worked on the dilute magnetic semiconductors. So most of the research we did on dilute magnetic semiconductors. So how you will get the dilute magnetic semiconductors means, so when you dope the actual 2,6 semiconductor in terms of the actual transition metals, those transition metals may be cobalt, nickel, and ferrous. So those are, we are adding those materials in very little into that of the 2,6 compounds. When you take the zinc sulfide, cadmium sulfide, zinc oxide, copper sulfide, so we will take the compound like this. In this compound, what we will do is we will add little amount of the these transition metals or in terms of the rare earth elements. So after addition of these materials, doping those materials into these 2,6 compounds, what you will get is you will get the magnetic phenomena. So this is called the dilute magnetic semiconductor because we are adding little amount of the dopant to 6 compound. So then we are getting the magnetic property. So this is named as a dilute magnetic semiconductor. So in this one, when you take in terms of the copper sulfate, in this one, actually, when you take the cadmium sulfate, zinc oxide, all these materials in the bulk form, so they are in terms of the diamagnetic property. So when you grow the same materials in terms of the nano form, some are exhibiting the actual ferromagnetic property because of the size and interactions. There spin, we have the alignment of the spin is taking place in terms of the nano materials. So when the material, if the material is in the bulk, when you take it is diamagnetic, the same material in the nano form, it is exhibiting the ferromagnetic property also. So we have so many materials like that we verified. So when you, the best material that is exhibiting like that is zinc oxide among all the 2,6 compounds. So in this one, we tried in terms of the copper sulfate. So here the copper sulfate is diamagnetic in terms of the, when you take as it is as copper sulfate. So when you dope the copper sulfate in terms of the ferrous, so this is the flow chart. So that is explaining us how you can add the material and how you can get the actually the copper sulfate doped nanoparticle. So like this, we can grow the variety of the actual compounds with in terms of the different dopants also by using the chemical purification method. So like this, we can obtain this one. So this is the actually the same micrograph. So that is telling us. So these are different. So this is with a different. So the doping concentration is varied. So in this one, A is with one doping concentration of the ferrous. So here we synthesize copper sulfate with different doping concentrations of the ferrous. So we have used only the one capping agent for all these four. So based on the doping concentration also, the actually the size of the particle is changing. So all these things are affecting to get the particle size. So the particle size depends upon the what is the capping agent that we have used to grow the particular particle, and it also depending upon the what is the concentration of the dopant that is used. So all these things are playing very major role in size of the particle. So we have the four pictures here. In this one, four are not with the same particle size. So the particle size is varied just because of the ferrous that is added to the material. So like that, we have the four pictures in here. We have the this one. So here, this is actually the what is the magnetic property what we have obtained after growing the copper sulfate with respect to ferrous. So we doped the copper sulfate with the ferrous. So in this one, we have studied the ferrous in terms of the 0.01, 0.03, 0.05, and 0.07. Then we took the VSM. So in this one, we have the studies its loop like this. So when you take the pure cadmium sulfate, so it is not exhibiting the ferromagnetic behavior. So as soon as the copper sulfate is doped with the actual ferrous, so it is exhibiting the actual ferromagnetic behavior. So like this, this material is not in the actual whole form, it is not exhibiting the ferromagnetic property. So when you dope that one in terms of the ferrous, it is exhibiting the property. So why we have chosen this actually the dilute magnetic semiconductor means these are having applications in terms of the spintonic devices. So because of that reason, we worked in the field of the actual ferromagnetic materials. So this is the how you can get the ferromagnetic property in terms of the doping of a particular compound like this. So next method which I am going to cover is the hydrothermal or the solvothermal method. So this method is also is with less expensive. In this one, this method is also same as that of the chemical precipitation method. So the reaction, the actual materials that were used for the chemical process, the same materials that can be used in case of the hydrothermal method also. So the other thing what we will do in the case of the hydrothermal method is, so we will use the autoclave. So what is the reaction solution what you have obtained in the chemical precipitation method? So we will use the same reaction solution. So we will pour that one in terms of a autoclave. Then we will maintain the autoclave at a certain temperature by using the muffle furnace. So here by with that one you will get the, so what is the difference in terms of the chemical precipitation method and the hydrothermal method? So the important thing what we should be noted here is, in the case of the chemical precipitation method, so it is not possible to get the nanostructures with desired shape and size. So in the case of the chemical precipitation method, there is a possibility only to get the nanoparticles. So there is no chance to get the nano structures in terms of the nano rods, nano wires, and nano flakes like that. So in that one, the growth process is like that. So because of that reason, in the case of the chemical precipitation method, there is no possibility to get the nano structure form. That is a thing in the case of the chemical precipitation method. So when you use the same solution, to get the nano structures, what you can do is we can go for the solvothermal method. In this one, what we will do is we will take the reaction solution in the autoclave and we will maintain certain temperature in the furnace. Then after maintaining certain temperature, the growth process is starting. So with that growth process, we can get variety of nanostructures in terms of the hydrothermal method. So that is actually the advantage in terms of the hydrothermal or the solvothermal method. In this one, we can get variety of nanostructures. That is the difference between that of the chemical precipitation method and the hydrothermal method. So that means we are creating certain pressure by using a autoclave, by using the temperature. So with that pressure, the structures are developed. So that is the difference in the case of the, when you take in the precipitation method, we are not keeping that one in the with a particular volume vessel in the furnace or not. We are just heating the sample at the open atmosphere. So, but that is not the case in the case of this hydrothermal method. We are using the actually the autoclave so that we are fixing the volume. So we have the pressure that is built up with the temperature. So we are getting the required structures in the case of the hydrothermal method. That is the thing. This one. So this is the one composite we have prepared in our laboratory. So in this one, we have the composite is cadmium sulfate, molybdenum sulfate, selenium sulfate. That is the composite. So we have prepared so many composites. I am taking one composite to explain how you can use the solvothermal method to get the composites also. So in this one, to get this one we have the cadmium sulfate rods. Earlier we prepared the cadmium sulfate powder by using the chemical precipitation method. So with the same solution, what you can get is we can get the nano rods in terms of the solvothermal method. So that is the difference between that of the chemical precipitation method and the solvothermal method. So here we can get the nano rods, nano structure depending upon the temperature what we have used applied to a furnace and how many hours we kept that autoclave in the furnace, that all plays major role to get the different structures. So all these things are to be tailored. So we have to tailor the parameter to get the required structure based on the temperature what we have applied and how time, that plays very important role to get different types of the variety of the structures. So in this one, we synthesize the cadmium sulfide nanorods by using the solvothermal method, and the reaction process is same as that of the chemical precipitation method, but we have used the autoclave, and by using the autoclave, and we obtain the cadmium sulfide nanorod. So then we synthesize this one in terms of the, we have the molybdenum sulfate. So we synthesize the nano flakes of the molybdenum sulfate also by using the hydrothermal method. Then we synthesize the selenium sulfate. The selenium sulfate are also we synthesize by using the hydrothermal method only. So in this one we obtain this type of structure by using the selenium sulfate. So we have the molybdenum sulfate, we have the cadmium sulfate. We have the three products, that means three compounds we obtained by using the solvothermal method. So we have used the autoclaves to different size autoclaves to obtain this structure. And we already mentioned what is the temperature which was kept at. So we have to all these things we have to find out through the literature, or we have to do it in terms of the trial and error procedure. So by using the trial and error procedure also we can do is we can tailor the properties. So here we have used this one in terms of the 160 degrees 48 hours to get the nano rods. Here it is the 220 degrees and 24 hours. Here they also use 220 degrees and 24 hours. So like that, by maintaining the different temperature and the time, we obtain the nano rods and nano flakes and the powder. So like this, we obtain 3 compounds. So what we did in our laboratory is we prepared the nano composite. So to prepare the composite, the process we adopted here is the ultrasonification. So we have the cadmium sulfide rods. Then after ultrasonification with molybdenum sulfate and selenium sulfate, we obtain the composite. That composite is nothing but the cadmium sulfide, molybdenum sulfate, selenium sulfate, nano composite. So like this, we synthesize the nano composite in our laboratory. So here, and this is actually the synthesis process as per the salvothermal. So why I am explaining all these things here is, so this salvothermal method is a very good method to get variety of nano structures. So we have the CVD also. CVD also I am going to explain at last of this lecture. So when you take the CVD and compare this one, this method is very simple compared to that of the CVD process. In the case of the salvothermal method, we can get variety of nanostructures. So that is the thing that is to be noted as far the salvothermal method is concerned. So in this one, so these are actually the some micrographs of so we synthesize the rods and the flakes and the powders by using the salvothermal method. So when you observe what is actually the morphology of the actual cadmium sulfate, molybdenum sulfate that were synthesized were obtained. So in this one, this is actually the cadmium sulfate. So after synthesizing, we got the actual nano rods in terms of the cadmium sulfate. So this is the molybdenum sulfate. So molybdenum sulfate actually it is in terms of the layer structure. So this is the molybdenum sulfate. That is the structure what we have obtained in terms of the molybdenum sulfate. So next one is we have this is actually the selenium. Cobalt selenide. So here this actually there I have shown that one as the selenium sulfate. We have did many things in this one. We have cobalt selenide. So this is cobalt selenide. So this is the composite what we have obtained by using these 3 things. So in this one, this is actually the cadmium sulfide versus molybdenum sulfide, cobalt selenide, nano composite what we have obtained after ultrasonification of the 3 materials for certain temperature and time. So that is the thing what we, so like that we can grow variety of structures by using the salvothermal method. So this method is very useful to get the variety of the nanostructures. So next one is we have the sol gel method. So this is also with less expensive. It is also same as that of the chemical cold precipitation method. So in the what is the difference here is we will the sol gel method is having more advantages than that of the chemical cold precipitation method. So in this one we will form the colloids with the same compounds what we have used for the chemical cold precipitation method. So in this one what we will do is we will use other actual organic solvents for like that of the tartaric acid and that. So by using that one, what we will do is we will get a colloidal solution. So in this one, this is also let's say control upside high purity. So it is easy to maintain stoichiometry. So there is no question of the requirement of the sophisticated instrument. So what is the operator that we have used to synthesize the chemical co-precipitation method? The same operators that can be used to synthesize the nanomaterial in terms of the sol gel method also. So in the case of the sol gel method, we have the gel in terms of the solution. So how to get the gel means we have the liquid. So that is to be, we have the process here is hydrolysis and condensation. So this is the process that is to be, that is the case in the case of the sol gel method. So here in our lab, we synthesized bismuth ferrous oxide nanoparticles by using the sol gel method. So what is the thing we noticed as per the bismuth ferrous oxide is concerned? So we synthesize bismuth ferrous oxide by chemical cold precipitation method, and we synthesize the bismuth ferrous oxide in terms of the sol gel method. These both methods we have used to synthesize the bismuth ferrous oxide nanoparticle. So what we have noticed in the final product here is, so the bismuth ferrous oxide we synthesize in terms of the chemical co-precipitation method is in terms of the mixed process. So we tried to synthesize bismuth ferrous oxide for many times in terms of the chemical co-precipitation method, but all the times we got the mixed phases in the case of the actual crystal structure is concerned in terms of the bismuth ferrous oxide. Then we switch out the procedure from chemical precipitation method to the Sol-Gel procedure. So in this one we added the tartaric acid. That is in this one this is the procedure that we have used to synthesize the bismuth ferrous oxide in terms of the Sol-Gel method. So in this one, after final product, in the final product we didn't notice any mixed phases after synthesizing the bismuth ferrous oxide in terms of the Sol-Gel method. So that means when you compare the chemical precipitation and the Sol-Gel method is suitable for certain material and chemical precipitation method is suitable for certain material. So in the case of the Sol-Gel process, the procedure is somewhat different from that of the, in this one we have the gel formation is there we have the precipitation formation. So with that gel we can get the final product. So there is a difference between that of the chemical precipitation method and the Sol-Gel method. So like that we obtain the bismuth ferrous oxide material in this one. So actually, so when you observe the block diagram in terms of the when you see how the process takes place as far the Sol-Gel process is concerned, so we have the metal alkoxide solution. In this one, the process is in terms of the hydrolysis and polymerization. So we have the salt, we have the gel in terms of the solution. This is the salt formation. So in this one, when you have this salt, so what you can do is we can get the variety of things in this one also. So when you want to make it as a powder, we can make it as a powder. When you want to make it as a pellet, we can make it as a pellet. And when you want to make it as a film, we can make it as a film. So this is the advantage in terms of the Sol-Gel process. We have the gelatin is formed, so we can transfer that one to required shape or size depending upon your requirement. So like that we can form different varieties of things by using the Sol-Gel. So this thing that is not possible in terms of the chemical precipitation method is concerned. So there we will get only the precipitate, that is in terms of the nanoparticles only. But in case of the Sol-Gel process, so we can coat the gel at any place by using the process, so that we can get the required, actually we can use this one for required dimension and shape. Like that we can get the thin films or actually the pellets, or in terms of the powder, or in terms of the particles. So whatever form you want, you can do it by using the Sol-Gel method. So that means the Sol-Gel method is also a less expensive method. We can get variety of materials by using the Sol-Gel method. So this is actually the process how you can form the materials by using the Sol-Gel method. So this is the procedure that is to be taking place in terms of the Sol-Gel process. So in this one, this is the actually the same diagram of the bismuth ferrous oxide. So we prepared the pure bismuth ferrous oxide. We dropped the bismuth ferrous oxide in terms of the NPM. So actually in our lab we synthesized the bismuth ferrous oxide by doping with calcium, ferrous and all. So we synthesize many compounds in terms of the bismuth ferrous oxide also, because bismuth ferrous oxide is a multiferroic material. That means it exhibits both the ferromagnetic property and the ferroelectric property. So the both properties are coexisted in a single material. The best material in terms of the multiferroic is in terms of bismuth ferrous oxide. So thus we synthesize the bismuth ferrous oxide in terms of the different dopants also. So this is the actually the same diagrams that is showing us the bismuth ferrous oxide in terms of the erbium with the different concentrations. Erbium is we have moved into the bismuth ferrous oxide method. So we obtain different actually the same diagrams in this one. So this is the actual ferromagnetic property. So that is
Professor Vijayalakshmi ma'am.
Oh, okay, ma.
Gentle reminder, ma'am.
Okay, ma.
Yes, ma'am. Thank you.
So, okay, this is the ferromagnetic property what we have obtained in terms of the bismuth ferrous oxide. So, next one we had a chemical vapor deposition. This also we tried in our lab. We obtained variety of structures So in this one, this is the experimental setup that is used to grow the variety of nanostructures in terms of the chemical deposition. This is somewhat costly compared with that of the apparatus in terms of the chemical purification method, hydrothermal method, and salt gel method. So in this one, additionally, we require the rotary pump, and we require the tubular furnace, and we require the argon gas also to control the flow. So all these things in additionally required in terms of the chemical vapor deposition. So this is the actually the block diagram that is showing us how you can get the different variety of structures. So these are the structures which we have grown in our laboratory by using the chemical vapor deposition method. So these are the structures we have grown. In summary, what you can do is we can grow variety of nanostructures by using solvothermal method and chemical vapor deposition method. So when you want to go for a chemical, actually nanoparticles, we can go for chemical precipitation method or salt gel method. When you want to grow for a different variety of structures, what you can do is we can use the solvothermal method or the chemical vapor deposition method. So when you compare the chemical vapor deposition method and the solvothermal method, solvothermal method is somewhat less cost compared with that of the actual CVD method. So this is the point which I want to mention. Okay, I thank the organizers for giving me this opportunity to speak on this workshop.
Thank you so much, ma'am. Now I request all the participants, if you have any questions, you can interact with the ma'am for 1 or 2 questions, and other questions we can direct it to ma'am's mail.
Madam,
Sir,
Madam, you told 5-6 methods on that one. How it will be environmentally and also processing parameter size and also impurities wise and also mass production wise. Can you tell me any for this one any explanation, madam?
So mass production.
Also 1 gram to synthesis 1 gram, how much cost will be?
So you can use the chemical precipitation method, sir, when you want to produce in terms of the mass production. Disturbance.
yes, ma'am. Yes.
Disturbance.
No. Yes, ma'am. Sir Subramaniam, sir, did you get your answer, sir? Okay. Oh.
Please, 1 gram synthesis above meters, how much cost will take? That is my question. One thing, madam.
1 gram synthesis.
Okay, ma'am, his question is if
1
we are
gram of
prepared.
material to synthesize, how much cost expenses?
Yes.
It's less than, I think it is less than 1,000 rupees.
For 1 gram.
1 gram. Yes, sir.
And also environmental.
Sir, actually we won't get any impurities in this method also, sir. Impurities are very less. No impurities actually. We didn't find any impurities in our samples. What we have synthesized so far.
Hello, ma'am. I have a question.
Leaf powder.
We have not synthesized, sir, in terms of green synthesis. We didn't prepare any samples by green synthesis in our lab. We only with chemicals only, not leaves and all.
Thank you so much, ma'am. Maybe so many people are eager to know and discuss with you some more questions. Maybe I'll request you, if in your free time, kindly respond to those queries and give the answers through email, ma'am. So due to time lag, yes, ma'am. Due to time lag, I'm just ending this wonderful talk at this particular moment. So thank you so much, ma'am. It was so informative, and we could see all the theory how the nanomaterials can be very easily synthesized by any basic laboratory without much technical advancements. Still, we can do that, and that too not without utilizing much of the expensive things. Yes, ma'am. So that was wonderful to know for any non-nano person to enter into nano research, which is very much necessary right now. Thank you so much, ma'am. It was so informative. You gave us with the case studies also. Excellent talk, ma'am. Thank you so much. Thank you for being
Okay.
on this show, ma'am.
Thank you, Dr. Mamata and Professor M.V. Shankar sir, for giving me this opportunity to talk on this workshop. Thank you so much for the
Yes.
organizers.
Thank you, ma'am. So now
Okay.
I request all the participants. So now we go for the next final talk of today's session, and that I request my colleague, Dr. B. Vijay Kumar Naidu, sir, to introduce next speaker to the participants.
So good afternoon, everyone. I'm happy to introduce the next speaker, Dr. K.K. Charlatan. Presently, he is working as associate professor at VIT. And before that, he has some postdoctoral experience from Korea and also from Japan. And he did his PhD from Anna University. And he has having some memberships in IJDA, SACSE, and Indian Science Congress. And his research interests focus on geolites, mesoporous materials, carbon materials, and heterogeneous catalysis. And successfully guided 2 students for doctoral degree and presently working 5 students with him. And to his excellent career, he has published about 46 peer-reviewed journals, and he has also published 3 books, and he has given a number of invited talks at various conferences and symposia across India and also other countries. At this point, I welcome Dr. K. Charlatan to present his work today. Thank you.
Thank you, Dr. Vijay. Can you hear me?
Yeah. Mamata, please share the link.
Yes, we can hear you, sir.
Okay.
Yeah. Now I share my presentation. Is it visible?
Yes, sir.
Yeah,
We can see
it's
it.
visible.
Okay. First of all, I wish to say my thanks to the organizers of this workshop for giving me this opportunity to speak in front of you. Now I am standing between you and your lunch. Okay, please bear with me. I will try to finish my talk as soon as possible. I think I have 30 minutes. Is it that?
Yes, sir. 30 minutes. Yes, sir.
Okay. Thank you. Fine. So good afternoon, everyone. So my talk will be about hierarchical geolites, structural design, and catalysis. This will be the flow of my talk. From the organizers, I came to know that there are many students, so I included some basics of geolit chemistry, and then I will talk about limitations of condensate geolites, and then advantages of hierarchical geolites, and then I will show you some methodologies to synthesize these hierarchical geolites, and then also I will discuss about some catalysis, and I will include some examples from literature and some work from our group. What are geolites? Geolites are crystalline aluminum silicates, and they are widely used as catalysts, as adsorbents, and also as ion exchanges. And if you look at these geolites, they are made up of silica and alumina. They contain silica and alumina, and the silica and alumina ratio can vary from 1 to infinity. And the specialty of this geolites is that they have exchangeable cations. There will be alkali cations, and they can be exchanged by protons. So because of that, the geolites are widely known as solid acid catalysts Particularly these zeolites, if you look at, they are crystalline and they are microporous in nature. And they have channels and cages. So here I have shown some of the zeolite structures for the site LTA and MFI. So you can see some cages here. I'll use the pointer. Yeah, you can see the cages and channels, okay, which are formed in the structures. So these kind of channels and cages, they form like micropores in these materials. Okay. So when I talk about porosity, so many students they may not understand what is a micropore and what is porosity and all this. So for that, I thought of showing this slide to you. So porous materials can be classified based on this IUPAC nomenclature. So based on this IUPAC nomenclature, they can be called as microporous, mesoporous, and macroporous. So in the case of microporous materials like zeolites, the pore diameter or pore width will be smaller than 2 nanometer. So the materials which are having pores smaller than 2 nanometer, they will be called as microporous materials. And then the materials which are having widths greater than 2 nanometer and within 50 nanometer, they will be called as mesoporous materials. And then if the pore width is greater than 50 nanometer, they can be called as macropores. And if you look at this microporous and mesoporous materials, they can also be called as nanoporous materials because the pore width is falling within 50 nanometer. Some people even they call them as nanoporous materials. And the zeolites, which about which I am going to talk about, so these zeolites are microporous, and essentially they are nanoporous based on this classification. And the picture which is shown here, it is nothing but a cross section of a porous solid, an hypothetical porous solid. It's not a real solid, which is having different types of pores. So here, this classification only talks about the pore width. Okay? Apart from the pore width, the pore shape also important. So this cross-sectional image, the different types of like shapes of pores are shown and their names are given. They can be a cylindrical pore like this. So if it is looking a cylinder, then it is called a cylindrical pore. And if the pore is closed one, it is not having any connectivity to the upper surface, then it is called as a closed pore. And if the pore is looking like a funnel, it can be called as a slit pore. And if the pore is having a narrow mouth, pore mouth, and wider pore, then it can be called as in-portal pore. Like that, we can classify porous materials, and essentially, these zeolites are microporous materials. And when we talk about this kind of porous materials, how to know whether a material is having micropores or mesopores or macropores? So we need some characterization techniques. Often, nitrogen adsorption and the mercury porosimetry are used to characterize this kind of porous materials. For characterizing microporous materials and mesoporous materials, people generally use this nitrogen adsorption technique. So this is a typical nitrogen adsorption isotherm of a material which is having both micropores as well as mesopores. So how to know a material is having micropores? You have to look at the lower p-pi-p0 value. Okay. This region, if you have a knee, okay, a bend like this in the isotherm, then you can say that there are micropores. And if you have hysteresis or this kind of increase in the absorption in the wider, in the higher p-pi-p0 value, then you can tell that it is having mesopores. So by this way, by using nitrogen adsorption method, you can characterize these porous solids when they are microporous or mesoporous. Not only this, from this isotherm, we can also calculate pore size distribution. I didn't show the pore size distribution curves here, but it is possible. In the case of macropores, this ideal assumption alone, it cannot be like giving you an exact picture. So people will go for mercury porosimetry. So in this case, in the case of mercury porosimetry, mercury will be pressurized into the pores, and based on this intrusion and extrusion curves, this is the intrusion curve, and this is extrusion curve. People will characterize the macropores. So by using the combination of this nitrogen absorption isotherms and mercury porosimetry, one can characterize mesopores as well as macropores. So this is about characterization of this porous materials. And then coming back to zeolites, how are zeolites formed? That is the next question. So as I told you, zeolites are made up of silica and alumina. So the silica and alumina, they will be in the form of this tetrahedra. So several tetrahedral units of this SiO2 and Al2O3, they are called as primary building units. So they will join together and form secondary building units. Then the secondary building units will form a polyhedra like this, which will be finally ending up in forming a zeolite structure. So when this structure is formed, you can look at they are this polyhedral like structures. They are arranged in a particular fashion, and they lead from cages and channels. Okay. So in order to direct this formation of this kind of structure, we need structure directing agents. There will be some molecular templates they will be used to form this kind of structures. Okay. And then, why are zeolites are popular as catalysts? Zeolites are having acidity. They have acid sites. So typically, if you tell the name zeolite, then it is known as a solid acid. So they have Lewis acidic sites and Brands acidic sites. And beauty is that this Lewis and Brands acidic sites can be tuned, okay, by modifying the silicon ratio, or by modifying the cation. We can play with this acidity, and it is tunable. That is advantage of this solid acid zeolite. And then not only that, they show selectivity. They exhibit reactant selectivity, product selectivity, and transition state selectivities. So during a reaction, if you need selectively a product, then you can go for a catalyst like zeolite, because by choosing a particular type of zeolite, you can obtain a particular product selectively. It is possible. And not only that, by incorporation of other metal sites. Okay, I told you that zeolite will have only silicon and alumina, but you can replace aluminum or silicon by other metal sites, and by this way you can incorporate different functions like oxidation, reduction. Even basic zeolites can be prepared by playing with this kind of metals which are added to the zeolite structure. And finally, they are all crystalline. They are very stable at higher temperatures, and they are crystalline. So due to all these properties, the zeolites are popular as catalysts. And why these zeolites are acidic? What is the origin of acidity of this zeolites? That's what I'm going to explain in this slide. So if you think about only silica framework, okay, it is made up of only silicon and oxygen. You won't have any acidity at all. It is a neutral framework. Okay. But when you incorporate aluminum into this framework, as shown here, what will happen? There will be extra negative charge. So this extra negative charge should be compensated. So if you compensate this extra negative charge with proton, then the solid will act as a Francis acid. And not only this proton, you can have sometimes sodium, potassium, even cesium, replacing this kind of cation. So in that case, accordingly, the nature of this solid can be varied. So if you have cesium, then you will have more of basic sites in the zeolite. Completely, the property of the zeolite from acid, it will become basic. That is possible. So not only constant acid sites, also Lewis sites can be generated in the zeolites. So when you heat this framework, which is having silica and alumina, when you break this bond, okay, you will have this kind of tri-coordinated like aluminum, which is similar to that of AlCl3. It can act as a Lewis acid. So in a zeolite, you can have branched acid sites as well as Lewis acid sites. So that is why these materials, zeolites, are attractive acid catalysts. So when you talk about acidity, how to characterize this acid sites? Because in the case of liquid acids like sulfuric acid or hydrochloric acid, in the lab we can titrate and find out its strength. But in the case of solids like this, how to study the acid sites? How to find out the acid strength? So there are some techniques. So this temperature programmed desorption of ammonia is the widely used technique to know the acid sites and acid strength of the zeolites. So here, based on the temperature at which the absorbed ammonia is desorbed, we can tell whether it is having a weak acid site or a strong acid site. So initially, ammonia will be absorbed on the material, and then it will be desorbed by increasing the temperature. So in the x-axis, I have temperature, and then the y-axis desorption rate. So based on the temperature at which this desorption takes place, we can tell whether material is having strong acid sites or weak acid sites. So the temperature, the higher the temperature of this desorption, the stronger will be the acid site. That is the idea. And not only that, we can also quantify the acid sites. So the area behind the area below this peaks, they can give you an idea of the amount of acid sites present in the material. So this kind of temperature program, the desorption of ammonia is used for this purpose. And then if you look at this technique, it is not going to differentiate between Lewis sites and Nano sites. So in the previous slide, I told you that zeolites are having both branched sites and branched sites and Lewis sites. How to identify them and differentiate them and quantify them? So in this TPD of ammonia, it is not possible. So because of that, we will go for in situ pyridine adsorption. It is a widely used technique, and by absorbing this pyridine on the catalyst and taking the FTR spectrum, people will characterize the branched and the Lewis acid sites. Okay. Typically, if there is a branched acid site in the material, it will have a peak at 1540, approximately at 1540 centimeter inverse. And in the case of Lewis sites, it will show a peak at 1450 centimeter inverse. And by quantifying the peak area, we can tell there are some methodologies to calculate the number of Lewis sites as well as branched sites. Here I am not going to discuss all these details because of need of time. So this is what it is. Then I told you that zeolites exhibit selectivity. So they can exhibit reactant selectivity as well as product selectivities. So these are the three types of selectivities which are exhibited by different zeolites based on the shape and size of the pores which they have. For example, in this case, I have a linear alkane and branched alkane. And in the case of linear alkane, it is easily passing through the pores because the size and shape of the pores, they are allowing this molecule to easily pass through it. But in the case of this branched chain alkane, it is not able to pass through. So by this way, this zeolite is imposing reactant selectivity. And not only that, even it can exhibit transition state selectivity. For example, in the case of alkylation of aromatics, there is a possibility that this benzene ring will be alkylated in multiple positions. In our normal conditions, if you perform the reaction in a liquid state, in a beaker or we perform this reaction, what will happen? In the multiple positions, it will be alkylated as shown here. Okay. But if you perform the same reaction on a specific zeolite, what will happen? Selectively, you can have a monoalkylated benzene. It is possible. It is happening because of the restricted constant state, which is formed inside the micropores of the zeolite. And also, this kind of product selectivities is possible. For example, if you alkylate toluene, this alkylation may take place in ortho position, meta position, and para position. Okay. Generally, it will take place like that. But when you perform the same reaction in the micropores of zeolite, what will happen due to the restrictions induced by the pore, you will selectively get this para alkylated product. So this kind of product selectivity is possible. So that is why zeolites are attractive like materials as catalysts. So you can understand how a zeolite is catalyzing the reaction. For example, you can take butene isomerization into isobutene. Okay. So I have a zeolite here, this zeolite theta, and I have channels, I have cages here, and in the channel or cage, I have a bronzer site. You can imagine this as a bronzer site. It is the active site, isn't it? It's the active site. So when the molecule is like approaching, it should enter into the channel and reach the active site or acid site, and then only it will be converted into the product. So essentially, the reaction will be controlled by the pore-section cell because the active sites are present inside the material, inside the cages or channels. Okay. So if you want to do the catalysis, or if you want to modify the properties of the zeolite, you should take care that this acid sites are not disturbed. Okay. So this kind of because this kind of setup, this channels along with this acid sites, okay, they give this product selectivity as well as catalytic ability for this material. Okay. So you can, in order to give you a view how a zeolite is catalyzing the reaction, I have given this example here. And then because of this kind of catalytic properties, zeolites are used widely in petroleum processing. So this flow chart shows in different processes where in different places these zeolites are used. All these gray colored processes, okay? FCC, fluid bed catalytic cracking, for example, okay? Degaxing, okay? Isomerization. Like this, in all these processes which are involved in petroleum refining, they use zeolites. Not only that, zeolites are also utilized in different other reactions. So if you look at the progress of zeolite catalysis, there are many matured technologies. For example, fluid bed catalytic cracking. It is already matured, and in the industry, they are using this kind of technology and producing products. And then ethanol to gasoline, ethanol to gasoline process, ethyl benzene alkylation, paraffin isomerization. These are all mature technologies. And also there are research efforts which are taking place. And in the case of developing new technologies based on zeolites, for example, hydrocracking, hydrogenation, butane isomerization, they are in the developing stage. And also there are many other technologies which are related to auto exhaust cleaning, denox catalysts, iso degaxing. All these are emerging technologies which are based on this zeolite catalyst. Not only this in the industrial catalysis, also in the fine chemical synthesis, people are using zeolites. There are plenty of publications available in the open literature talk about applications of this zeolites in several organic transformations and as well as fine chemical synthesis. So it's no wonder that zeolite is a wonderful catalyst, but it has some limitations. Okay? Because if you look at the zeolite structure, they are essentially micropores. So the pore size is below 2 nanometers. So you cannot use zeolites to process molecules which are larger than 2 nanometer. That is one of the limitations of zeolites. Simply, you can understand this by looking at this slide. If you will take a zeolite which is having like MFA zeolite is having a pore width of about 0.54 nanometer, and if you pass toluene, toluene easily pass through the crystal, zeolite crystal, and come out. Via the pores, it will enter and then it will come out. Okay? It will diffuse into the catalyst crystal of this zeolite. But at the same time, if you think about cholesterol, which is a larger molecule, it cannot be processed by the zeolite because it won't enter into the pores at all because of its larger size. Okay? So this is one of the main drawbacks of this zeolites. So when we talk about diffusion, so in the case of zeolites, intracrystalline diffusion is taking place. Okay? This kind of intracrystalline diffusion is taking place in the micropores. So it limits the bulky molecules, larger molecules which are having the size bigger than the pores, micropores. They cannot enter into the pores. Also, the smaller molecules, when they enter into the pores, they have some kind of restriction to flow through to diffuse through the pores. But in the case of larger pores like macropores and in the case of mesopores, this kind of molecules, both bulky and smaller molecules, they easily diffuse into the material. Okay? And graphically, if you want to understand this or explain this, you can have a graph like this. Okay? So what I have in this graph, pore diameter and the diffusion coefficient in the y-axis. So when you decrease the pore diameter, what happens? The diffusion coefficient, it is decreasing. In the case of macropores and mesopores, the diffusion coefficient is little larger compared to this kind of micropores because intracrystalline diffusion is difficult in the case of microporous materials like zeolites. So because of this limitation, the activation energy for diffusion, it increases as shown in this graph. Okay? When you decrease the pore diameter, the activation energy is increasing. In the case of microporous zeolite, like microporous material like zeolite, intercrystalline diffusion, it requires higher activation energy because of this difficulty difficulty experienced by the molecules to diffuse into the micropores. So it reflects in the efficient use of the catalyst. Okay? Because of this kind of diffusion restriction, what will happen? Only the smaller molecules, as shown here, okay? This ethylene, it is a smaller molecule compared to benzene. It easily diffuses into the pore, and because of that, the concentration gradient outside the crystal and inside the crystal both are same. But the product as well as the reactant, benzene, they face difficulty to diffuse into the crystal due to the process limitation. So what happens? Inside the crystal, the concentration of this molecule benzene is decreasing. At the same time, the product formed inside the pore, it is building up. Okay? The concentration of the product is building up inside the catalyst. So because of this, no, you cannot use the crystal of your zeolite completely. So only the surface of the crystal is utilized completely, and the inside part of the crystal is not utilized completely. Okay? So it is like you are buying a material, but you are utilizing only 30% of it. 70% of it is going waste. It is like that. in the commercial applications, it is not acceptable. So we have to improve the performance of the zeolite. How to do that? That is what we are going to see the forthcoming slides. So if you want to like calculate or find out the efficiency or effectiveness of a material, a crystal, while molecules are diffusing into it and undergoing a reaction, then we have to look at this Taylor modulus and effectiveness factor. Taylor modulus can be calculated by using this formula. This phi is nothing but Taylor modulus, and the effectiveness factor can be calculated from this Taylor modulus. It is nothing but rate of the reaction observed, rate of the reaction intensity. So what is this effectiveness factor? If this ratio between this observed rate and intrinsic rate, if it is 1, then you are using the catalyst 100%. Okay? Like that you can imagine. Okay? So it is nothing but tangent of this Taylor modulus divided by the Taylor modulus. Okay? So when you plot this effectiveness factor and the Taylor modulus, then you will get a graph like this. And based on the like position of based on the position in the graph, you can tell whether you have achieved a reaction limited condition or diffusion limited condition. Okay. In the case of reaction limited condition, the reaction is not controlled by the diffusion limitation. Okay. It's not controlled by diffusion. Okay. When a reaction is taking place, there will be an active site which is catalyzing a reaction, and it should be limited to that. In addition to that, if you have diffusion control, then there will be two factors: diffusion also controlling the reaction, and the active sites, availability of the active sites also controlling the reaction. We don't want that. Okay. For efficient use of catalyst, we need only reaction limited condition. Okay. And when you go for diffusion limited condition, what happens? The catalyst cannot be used properly. Poor use of catalyst will be there. That is what reflected in this picture. Then, how to overcome these diffusion limitations? Okay. So we have to increase the diffusivity. Okay. That can be done by shortening the diffusion path length. Okay. Because the diffusion limitation, this kind of like unexpected overuse of catalyst happens because of diffusion limitation. So if you want to improve this, then you have to improve the diffusivity. How to do that? You can do that by shortening the diffusion path length. So if you want to shorten the diffusion path length, in two ways we can do that. We can introduce additional porosity. Okay, already we have micropores in the zeolite. So additional porosity means you have to introduce mesopores as well as macropores. Okay. So if you introduce this kind of additional pores apart from micropores, which are intrinsic to zeolites, then they are called as hierarchical zeolites. Not only that, you can also reduce the particle size. In that case, they are called as nanozeolites. Okay. So the scenario can be seen like this. So how diffusion path length is decreasing, and due to which how diffusivity can be improved. That is what shown in this different pictures. So I have different scenarios. I have intracrystalline mesopores. You have to understand that if I tell that it is having intracrystalline mesopores, it's a zeolite. It's already having micropores. In addition to that, I have this mesopores. Okay. In the case of conventional microporous zeolite, if the diffusion path length is like this, which is shown in this red arrow, in the case of mesoporous zeolite, the diffusion path length will be reduced like this. In the case of intracrystalline macropores, okay, the conventional microporous zeolite is having diffusion path length this much, and because of the introduction of this macropores, it has reduced to this much. Okay. The same thing happens in the case of nano-sized crystals and nano sheets of zeolites, assembly of this nano sheets of zeolites. In all these cases, you can reduce the diffusion path length. So when you reduce the diffusion path length by modifying the size or by reducing the additional porosity, you can increase the diffusivity. That is the idea. See, in many ways it will be useful. For example, if you imagine the conventional zeolite is having only micropores, only the smaller molecules are diffusing inside the pores and bulky molecules are staying outside the surface. And in the case of the additional porosity introduced into the crystal, what will happen? Not only the smaller molecules are diffusing fast, at the same time, the bulky molecules, they can go and react with the active sites. So it was made possible by introduction of this mesopores as well as macropores. Okay. Ultimately, what will happen when you introduce this kind of additional pores? The difference in the concentration gradient.
Dr. Cheladam, sir.
Yeah.
Gentle reminder about the time, sir.
Yeah, how much time you have me?
Sir, maybe 2 minutes, sir.
2 minutes. Okay,
yes.
fine.
Yes, sir. Thank you, sir.
So when you introduce this kind of additional like porosity with mesopores or macropores, what will happen? The concentration gradient difference, what you have seen in the conventional zeolites, can be rectified, can be removed. Okay? So it will increase the catalytic activity. But you have to successfully synthesize this kind of mesopores zeolites or macropores zeolites. Okay? So that is where this design comes into picture. Okay? So there are different ways reported in the literature to design this kind of hierarchical zeolites. You have bottom-up approaches and top-down approaches. And some of the ideas I want to show you here. So you can have a cationic polymer, and you can build your zeolite crystal surrounding this cationic polymer. And ultimately, finally, when you remove this cationic polymer, you will get a mesoporous zeolite. This is an idea. And not only that, even you can use carbon aerogel. When you synthesize your zeolite inside the pores of carbon aerogel, then you can reduce the size of the zeolite crystal. And when you have this kind of uniform crystals, what will happen? There will be interparticle porosity. So they will be falling in the range of mesoporous range. So it can be called as a mesoporous zeolite. Not only that, you can reduce some carbon into the zeolite crystal and finally remove the carbon. Okay? So when you heat in the presence of oxygen, what will happen? All the carbon will be removed from the zeolite after formation of the zeolite. Then you will end up with a zeolite crystal with additional porosity. This is possible. Not only that, even you can remove some of the silicon and aluminum present in the zeolite by reacting it with an acid or alkali. Here, post-synthetic desilication of the zeolite is shown. So it is made up of silica, isn't it? It is having silicon and aluminum. So when you treat the zeolite with sodium hydroxide, what will happen? The silica will dissolve. So if you control the conditions, what will happen? You will have the zeolite with this kind of additional pores created. So this is post-synthetic demetallation. The previous things, during the synthesis, you are introducing something and removing. Here, after the synthesis of zeolite, you are removing some silica alumina to get the mesoporous material. We can use also templates like polystyrene, okay? And prepare a kind of structure like this, which is having a zeolite structure, microporous zeolite, is also having macro cavities, okay, as shown here. So like this, we have plenty of opportunities to design this kind of hierarchical zeolites. So this will reflect in catalysis. For that, I have some examples. For example, if you react one benzyl alcohol with another molecule of benzyl alcohol in the presence of acid sites, you can generate this dibenzyl ether. These are all probe reactions. Okay? Some of the organic chemistry colleagues, they will think that it's a simple reaction, but it is a probe reaction. for probing the acid sites as well as influence of pore size. People working in geolic catalysis, they will use this kind of simple reactions which are having like bulky molecules, reactants, and products. So this reaction has been done in presence of this kind of a base. Okay. So this, when you use this base, it will cover all the acid sites which are present on the surface. Okay. So it will selectively attach with the sites present on the surface. So the sites present inside the pores will not be affected by this. So you can effectively characterize the acid sites and the influence of the difference in the like porosity by way of introducing hierarchical pores can be studied when you perform the reaction after masking all the surface acid sites using this kind of ditersyl-butyl pyridine. So the people have studied different like hierarchical zeolites, nanozeolites, and pillared nanosheets, macroporous zeolite, and all this. So you can see when you have this kind of hierarchical like pores or nano size zeolites, the stability of the catalyst, the lifetime of the catalyst can be increased. Okay, this is conventional microporous. This is time on stream, and the lifetime is small. But if you have this kind of pillared layers, your lifetime is enhanced enormously. It is mainly due to this introduction of the hierarchical porosity and reduction of the diffusion pattern. Okay. So this will be reflected in other reactions also. For example, glycerol dehydration, acrolein and hydroxyacetone. People have studied this reaction and found out that when they have this kind of hierarchical pore structure instead of this kind of microporous pore structure, the catalyst stability is improved. Even though you have extensive coating after the reaction, the catalyst showed activity due to the presence of hierarchical pores. Like this, you can have a number of examples in the literature. From our group, we have done some work. One of the PhD students used agricultural waste to produce this kind of hierarchical zeolites. Okay. So he produced monolith, he synthesized zeolite with intracrystalline pores, and also he prepared hollow structures of the zeolites, and also he prepared nanoparticle assembly of the zeolites by using biomass, particularly used corn stem pith to do all these things. So these examples just swiftly I will show. So in one of the case, what we have done, we have used this stem pith of corn to produce monolith of zeolite, which is having all these three types of porosity: macro, meso, and micro. Okay. And this synthesis methodology, I will skip this. So in this same picture, you can see how this bare sorghum pit, which is a natural material, is looking like, and the zeolite, which is prepared using this as a template, is looking like. We just replicated the structure of this sorghum pit in the zeolite. Okay. So if you look at the scale, you can see we have all these macropores. Okay. These are all macropores, can be called as macropores. Based on the scale bar, you can understand that. Okay. This is a macropore. So if you look at the further characterization, you can see in the nitrogen resorption, we have mesopores, okay, and as well as micropores. So micropores are coming out from the zeolite structure, and this mesopores are coming out from the pores which are reduced by synthesizing this material in the presence of this natural material. Also, we have done mercury porosimetry to study the macropores present in this material, and we found that this material not only has micropores and mesopores, also has macropores, which is looking like this. Okay, wide pore and narrow pore mouth. So this mercury intrusion and extrusion curve covers the shape indicates this kind of arrangement. And also we have done TM analysis to find out whether it is having intracrystalline porosity or not. Yes, this is the jeweled crystal, and you can see this bright spots. They are all showing some pores are present on the jeweled crystal. Okay, we did a simple reaction, this involving bulky reactants and products. We found that this catalyst, which is having both macro, meso, and micro, it is performing better even than this mesoporous GSM plant. Okay. Because of the presence of combination of all these three types of porosity, it is showing better activity. So not only that, even we have prepared a zeolite which is having this kind of mesopores and then loaded petropolyacid. So nanoparticles of petropolyacid loaded into this silicalide 1, which is non-acidic zeolite. Okay. And some characterizations I will show. This shows how this additional pores are present on the surface of the zeolite crystal. Okay. And then TM image shows a channel which is passing from the surface to interior. In the conventional zeolite, it is not there. In the case of the zeolite prepared by us, you can see this channel. Okay. Then ideal absorption, of course, it indicates the presence of micropores as well as mesopores. Then this is after loading HPA, petropolyacid. So the petropolyacid is entering into all the channels and forming held by the support. Then we performed a reaction. It's nothing but esterification of glutaminic acid in the presence of bulky long chain alcohols, propanol, butanol, heptanol. All these alcohols were used to esterify this reaction. The esterification is an acid catalyst reaction, and this zeolite is performing this well. If you look at this, the 38% HPA loaded catalyst is showing almost equal activity compared to that of bulk HPA. Okay. This is the difference. This 100% HPA is only 38% HPA loaded on this zeolite. So that is where this difference comes in. And the beauty is that this catalyst was performing the same activity even after 4 recycles. Generally, HPA, petropolyacid, will be soluble in polar solvents, but after supporting this HPA on this particular zeolite, we found that it's not happening, and this material is catalyzing the reaction even after 4 recycles. And we confirmed the presence of this HPA using UDS analysis and as well as TM analysis. And finally, we did some like NMR study and found that in the case of the material prepared by us, when you support HPA, this completely dispersed. Okay, this is bulk HPA, and if you look at this minus 50.2 resonance, it's not at all present in the material which we have prepared. That means all this HPA, they are bonded to the silica surface. Okay? It gives stability to this catalyst. That is why it is not leaching out. And even we confirmed this by using SPS analysis. We found interfacial WO3 present in this material which we have prepared. Okay, by this way, we confirm connectivity. So like this, we also prepared halogeolates, and we found like ruthenium, this hierarchical zeolite is performing better than commercial zeolite. Okay. This is a hydrogenation reaction. We try to hydrogenate this carbonyl group, and then it will undergo lactonization and form this lactone. This is called as gamma valorolactone. It is having many applications. It can be used as a fuel as well as solvent. So we got this 100% conversion and 99% selectivity of this product. Even when we use 1% ruthenium. Okay? So in the case of commercial catalyst, it needs 3-8% ruthenium loading, but in the case of our material, it requires only 1% loading of ruthenium. It saves a lot of this precious ruthenium. Okay? So with this, okay, I would like to stop my talk, and I hope I have given you an overview of the applications of zeolites and how hierarchical materials can be prepared, and different methodologies I have shown, and also I have shown some examples from our own research. Thank you once again for your questions.
Thank you so
Thank
much,
all
sir.
the students and DST for the support and as well as experimental work.
Thank you so much, sir. It was an excellent talk on various hierarchical geolites. So now I request all participants to restrict to only one question, if at all anybody is asking. If any other questions are there, they can email and put it in a chat box.
I think it is lunchtime, so people are hungry.
Okay, so I thank all the participants for being so patient with us and for being so keen on learning and be here from first day to till now. So now I welcome you all to the valedictory session of a workshop on advanced materials for energy and environmental applications. I'm sure we had seen various invited talks from different sections of energy and environmental sectors. And the design of the workshop was also to ignite all the people to involve in materials research and to have a discussion on various aspects of that, and which we had very nicely. And so all these 3 days had been a wonderful, enormous bundle of knowledge about the pathway to research in energy and environmental applications by various experts, and participants also made it all these days to be days of learning. So now to this valedictory session, I welcome Professor D. Vijayaraghav Prasad sir, who is our chief guest for today's valedictory session, to give a valuable message on this thing.
Very good afternoon to all the participants, speakers, and the organizers present right here with me. I'm extremely delighted to understand this event has been overwhelmingly successful with the participation of people and academicians and from industry corners also. I also are given to the understanding that several things were discussed, including the roadmap to R&D for energy and environment. It will go? Okay. But I'm not able to see this. And also, it is extremely important for the departments to integrate among with the conventional departments, with the nanotechnology and nanoscience and the material science departments to evolve ideas and pragmatic issues to improve the R&D in these areas. I think that has been delved in this meetings. I do understand and appreciate that. I think with this, I thank the organizers and all the persons associated with this.
Yes.
Thank you very much.
Good afternoon to all participants, chief guest of today's validity function, Professor D. Vijayaraghav Prasad Garu, organizers of this 3-day virtual online webinar by the Department of Material Science and Nanotechnology. I am very much happy that I think during these 3 days, almost all participants interacted and enjoyed academically and professionally. And I think their deliberations and their debates must be out in the form of a book by the organizers, so as to strengthen this Yogi Yamuna University. Thank you all for successfully completing this 3-day virtual webinar. Thank you, one and all.
So, thank you, sir, for being here as a guest of honor and giving your valuable message. Now, I welcome Dr. Chelaran, sir, as a special guest, and he has been a constant support for this workshop to give his message. Yes, sir.
Respected registrar of the university and other functionaries, faculty colleagues and student friends, very good afternoon to one and all. In the outset, I congratulate the organizers of this workshop, Professor Shankar and Dr. Mamata Kumari, and the faculty colleagues of the department for successfully organizing this 3-day workshop, AMEEA 20. This kind of webinars have become a new normal during this pandemic situation. And this kind of webinars, they are giving an opportunity to meet the students, faculty, and scientists, even though they are far away from each other. I'm a frequent visitor to your university. On these various occasions, spanning for about 8 years, I witnessed the growth of the Department of Material Science and Nanotechnology, and also the university as a whole. In terms of facilities, quality of education, and quality of papers published, I have seen this growth, and there is no doubt that it is a fast-growing university, as Professor Shankar often mentioned to me. With this small note, I thank all the functionaries of the university, honorable registrar, principal, and other organizing committee members for this opportunity. Congratulations. Thank you.
Thank you so much, sir. Now, I invite Professor M.D. Shankar, sir, convener of the workshop, to give a vote of thanks.
So good afternoon, all the participants, respected dignitaries, the registrar, and the principal of Yogi Amara University College, my dear colleagues, and all other participants. Good afternoon, one and all. It gives me immense pleasure to thank, to give the thanks for the all the people who involved in this webinar on advanced materials for energy and environmental applications. So I like to thank first the Vice Chancellor of the University, Professor I. M. Surya Kalavati Madam Garu, for giving the constant support for all the activities in the university, particularly in the Yogi Department of Materials Science and Nanotechnology. I'd like to thank the vibrant registrar of the university, who gives always yes to the all the developmental activities in the university. And I'd like to thank our principal. Though he's a senior person, he's respectable and friendly to all the people in the campus, and especially to our department also. So I want to thank these people, and I like to thank the organizing committee members, my colleagues, Dr. M. Dr. M. Ramanohar Reddy Garu, Dr. S. Adina Reddy Garu, and Dr. B. Vijayakumar Reddy Naidu Garu, and my colleague Dr. M. Mamata Kumari, who is the convener. She put a lot of effort for this conference, contacting the various speakers, and she has the dream in all the ways to cover the academics, industry, research institutions, and also the gender. Everything she like to cover. So I think she made all the justification in this besides the subject as well. I like to mention a few highlights about this conference. So we have got a overwhelming response from the participants, different parts of the country and abroad as well. So we received more than 297 participants in our country. About 11 states are participating, including our Andhra Pradesh state, starting from Punjab and till Tamil Nadu. And we are glad to say that we have a few participants from South Korea, Turkey, as well as China. So we are glad to say that many institutes like IITs, NITs, Central Universities, Caesar Institute, deemed universities, engineering colleges, degree colleges, a variety of people are there, from the students, postdoc, MSc students, BTech, BE students, faculty members, scientists, everybody participated in this webinar. So besides this, we like to say the thanks to our sister departments like physics, chemistry, biotechnology, and bioinformatics, genetic genomics, and YSR Engineering College. So all those people are participating, both students as well as faculty members. And we wish to thank the University IT and networking team, Professor Y. Nazir Ahmed, Mr. Uday Prakash Reddy, Mr. Anil Kumar Reddy for excellent arrangements for this webinar. University PRO Cell, Mr. Dr. S.V. Subba Reddy, Dr. T. Suresh, Mr. Obleshu for excellent coverage. Research Scholars of Material Science and Nanotechnology, Mr. U. Borgav and Mr. V. Navakarteshwar Rao. And we thank all the speakers, as said, for inspiring talks. We got the very good feedback from the students lively. And many students, participants are enthusiastically asking the questions and interacted with the scientists, all the speakers. So the speakers also answered immediately. Some of the questions due to the time constraint unable to answer. So those questions were shared with the experts. They will be contacting you in a short while. So we like to thank the Nano TV, Mr. Hari Prasad from Hyderabad, for giving the live streaming of this program. And we learned that first day we are sorry that unable to connect with the Nano TV live streaming. And more than 123 participants were watched the Nano TV. Most important thing, I think is the advantage of this Nano TV. They have recorded all the talks are available. Even students who are missed during this conference presentation for one or other means, they can listen and they can interact with the people. So the first time the Yoga University did this live streaming with Nano TV. Hope the university will come with the more and more developments in near future. Thank you, Ananda. Jai Hind.
Congratulations, honestly. Thank you. Congratulations to all the department.